morning to one and all. I, Ranu Nayak, on behalf of Amity Institute of Nanotechnology, Amity University, Uttar Pradesh, and my co-coordinators of the event, Dr. Jagjeevan Mittal and Dr. Nidhi Chauhan, would like to extend a warm welcome to all the participants and the eminent speakers of this workshop on smart nanotechnology in societal applications. This workshop will cover scientific sessions on themes based on various sustainability goals as set by UGC and United Nations. The themes are use of nanotechnology in clean water and sanitation, use of nanotechnology in affordable clean energy and environment, nanomaterials and nanotechnology in good health and well-being, and some other aspects of societal sustainability. This is going to be a 4-day academic cum research-oriented workshop and is going to give a matchless scientific meet where 22 distinguished speakers from all over India and some of our institutional young achievers are going to deliver their talks. I'm sure we would all learn new ideas from each other, which would adapt to further improve our work in specific research areas. Well, before beginning any event, it is our tradition to take blessings from the God Almighty. So, with these words, let us begin the event by praying to the goddess of wisdom, Ma Saraswati.
Ma'am, can you share again? And please select the share sound option.
Just a moment. Yes, Govinji, what is it that is not done?
Ma'am, please select the share sound option while sharing. There is no sound on the video, ma'am.
इंक्लूड साउंड बटन को क्लिक कर दिया आ जाएगा.
Where from?
Rohit?
Now is it audible?
Yes. Yes. Please reshare.
धियो शारदे माँ अज्ञानता से हमें तार दे माँ। मुनियों ने समझी है गुणियों ने जानी, वेदों की भाषा पुराणों की वाणी। मुनियों ने समझी है गुणियों ने जानी, वेदों की भाषा पुराणों की वाणी। हम भी तो समझे, हम भी तो जाने, विद्या का हमको अधिकार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ।
Well, welcome back, ladies and gentlemen. Now, I would like to invite our director of the institute, Professor O.P. Sinha, for the opening remarks. Professor Sinha.
Thank you, Ranu. Respected dignitary, Professor Sundar Ratan, Dean Science and Technology Domain, invited speakers, resource persons, participants, ladies and gentlemen. Good morning to all of you and a warm welcome from Amity Institute of Nanotechnology, Amity University, UP Noida. I am very pleased at the head of the Amity Institute of Nanotechnology, Noida, along with my colleague, to present the value-added workshop, a smart nanotechnology for societal applications, to you all, which is important topic, that is the nanotechnology undertaken by our institute since 2002. As we know, tools and machines that are or maybe in the future used to solve the real world problem are considered to be the technology. We now live at the age where we are surrounded by the technology in the some way or the another way. The ever-changing nature of the evaluation of the science and technology field has efficiently made our life faster. The work that could have been taken days when technology was not around is now achieved within a few seconds. On the other front, advancement in the science, engineering, and the technology, especially when I am talking about the nanotechnology, in many spheres has without any doubt made our lives better than earlier time. We cannot refute the fact that the lives of each one of us is highly dependent on the scientific inventions and the modern day technology. Nanotechnology has immense application to meet 21st century challenges, and seizing the opportunity will define the shape of our future. And this workshop is an effort for a dialogue between all the stakeholders to achieve the goal. Technology came in form of the tangential and intangential property by exerting physical and the mental force to achieve something that added values. For example, a mobile phone is a tangible, and the network connection used by the phone is the intangible. Technology has taken its place as indispensable, wherein it has resulted in economic benefits, better healthcare, time saving, and the better lifestyle. Technological advancement has brought an end to the wooden toy era and replaced with the same by automatic car. Its effects of nanotechnology has been well observed in all spheres like medicine, electricity, aviation, information, computer, meteorology, physics, nuclear energy, space technology, defense technology, research, biotechnology, household, sports, jobs, tourism, education, infrastructures, agriculture, and numerous other fields as well. An introduction of such technological stride, ideas, and inventions to all these fields has brought a gigatonic level of the positive change in the current generation, and thus has provided them a variety of new and innovation opportunities. In India, technology has become the main source of the foundational and the creative developments. It has improved and brought some huge development not only in the Indian scientific world, including fight with the recent COVID pandemic, but also economical status worldwide, and has also created many new programs for our new generation to grow in this technological world. The maximum advantage has been seen in the educational sector. The more technological modification, the better benefit it provides for the students at the several educational levels. For instance, since many students find the normal lecture boring and the monotonous, the idea of a smart classes make them more engrossed in the same lecture that they are earlier found boring. The online classes during the COVID pandemic are the another success story of the application of the nanotechnology for the societal application. There are also some people who are in the opinion that technology spoil a person by making him stoic or reducing his physical activity, thus increasing the chances of various health problems. This section of the people supports the fact that the technological based society offers a kind of silver spoon to the people, so much so that in the end they are unable to solve their problem of their own. This kind of dependency put people in a horrifying condition where they are not at all self-reliant. Other set of the people who debate on this argument believe that technology continue to be a very significant part of our society. They support the fact that it is an indispensable part of our lives in the present scenario and will only help people for their betterment. It is immensely useful in providing the much needed knowledge to the student. All the great exchanges in varied arenas discussed above has been taken place due to the game-changing contribution of nanotechnology. Further, this is a technical and the cultural revolution. But one thing we must not forget is that all the innovations are made to help us, not to make us the victim of the technological world. Now that we have a quick and easy access of the vast reservoir of the knowledge through internet, we should make good use of it to solve the problem that we have around the world. So participants, let us all take a pledge today to only make the fair use of the technology for the realization of our goals and not making ourselves slave of the technology. I greatly appreciate and applaud the wisdom, great urge to further develop scientific and innovation talents, and most importantly, that in the nanotechnology for society, global sustainability, which is the theme of this workshop, which is an era with unlimited possibilities. And anyone engaged in this field can achieve whatever would aspire for, either it is prosperity, food, agriculture, health, energy, and the environment. To achieve these goals, it becomes strictly necessary that we continue in the same line and follow the international standard and begin and being an Indian, I would like to quote that Ano Bhadra Kravate Yantu Visvata, taken from the Rigved 189, which means that let noble thought come to us from all and every direction in the universe. The focus of this workshop will be on the different aspects of the nanotechnology for global sustainability, and hope next 4 days it will be rigorous discussion on advancement in this field. At last but not the least, I would like to thank our beloved and the visionary founder President Sir for his vision to start this institute in India even before any IIT or the university. For nanotechnology education, making its first nanotechnology institute of India. Thank you, sir, for your vision and blessing to the nanotechnology community. Thank you all, and I hope this workshop will be a grand success. Thank you.
Thank you, Professor Sinha, for such informative and motivational words. Now, moving along, let us all welcome the Science and Technology Dean of Academics of our university and a very dynamic personality and researcher, Professor Sunita Ratan. Welcome, ma'am.
Yeah, thank you, Dr. Renu. Dr. O.P. Sinha, HOI and Program Director, distinguished guests, program coordinators, our most valued invited guests, delegates, faculty, and students. A very good morning. Once again, it's my proud privilege to extend my warm welcome to you all to the value-added workshop, Smart Nanotechnology for Societal Applications. As Dr. O.P. Sinha has clearly elaborated the uses of the technology and how it should be used, right? But when we see that nanotechnology has got a major role when it comes to the development of the technology, right? So when we say smart nanotechnology for societal applications, we all know that after 20 years of basic nanoscience research and more than 15 years of focused R&D, applications of nanotechnology are delivering in both expected and unexpected ways on nanotechnology's promise to benefit the society. When we were very young, we used to hear the word nanotechnology, that it will revolutionize the world. But yes, we have seen it that nanotechnology has revolutionized the world, because it is helping us to considerably improve even many technologies in an industry sector, whether it is information technology, homeland security, medicine, transportation, or you can say human body, among many others. So when we say, I can give some of the examples for the participants who are present here, because when we say that, let's go for eyeglasses, computers, camera displays, windows, other services, to make them water and residue repellent, anti-reflective coatings, self-cleaning, we talk of nanomaterials. Even when we talk of fabrics, we can say smart fabrics. Again, we are talking of nanotechnology because these fabrics are now equipped with nanoscale sensors and electronics, with capabilities for health monitoring, solar energy capture, and energy harvesting throughout the movement. Similarly, when we go for automobile industry, we see cars, trucks, aeroplanes, floats, and spacecraft. It is lightweightness. When we have to go for lightweightness, we look forward to nanotechnology. Even in polymer composite materials, for example, you can say sports, right? We can say baseball bats, tennis, rackets, bicycles, motorcycle helmets, automobile parts, all are including this the knowledge of nanoscience and the nanotechnology. So even I can say you go to the biosector. When we say bioengineering of enzymes, it is again nanobioengineering we are talking of, because it will enable conversion of cellulose from wood chips, corn stalks, unfertilized perennial grasses. All are talking of the means where these wastes can be changed to the utility items or the value-added products through the inclusion of nanotechnology. When we are talking of, okay, ethanol can be converted into fuel. Yes, we are talking of nanocatalysts. Right. So even when we go to, let's go to another technology. When we say packaging, right? Packaging, again, we are talking of nanotechnology, because we are putting those coatings which are antimicrobial through the nanoparticles dispersed in the polymers. So this is what I want to say, that the topic of the value-added workshop is very, very apt. Because when we are saying nanotechnology for societal application, it is impacting every sector of society. Every sector. I can see that I cannot now think of any sector where I can say that nanotechnology is not there. Whether when we say the sciences, chemistry, yes, we are working on nanotechnology. You are working on with nanoscience. When we say physics, yes, it is working with nanoscience. When we say mathematics, they are getting the computational problems using the in the nanoscience. So this is what I wanted to say, that this topic is very apt. And when we say value-added course means that we want to add the value to the courses the students have already learned. Right, so they have done the courses in their course. Now this will add the values, because the nanotechnology students and even the students from physics and chemistry, this course is going to add greater values, because it is going to give you the key concept, the key insights, that how the nanotechnology can be used in their respective sectors. I would have, I think we can have the students from the engineering background, because in every mechanical engineering, or can say electrical engineering, electronics engineering, nanotechnology is playing a major role. So I have just gone through the program. It is rather dense and rich, offering a considerable variety of topics to be covered, where we can see that how nanotechnology is impacting the society. And I'm sure that learning for the participants in this workshop is going to be a life-changing scenario as far as their research in nanotechnology is concerned. I congratulate Dr. Opisana along with his team, which is very motivated and dedicated colleagues who could invite the speakers and who could plan the whole program. And I conclude here with the belief that the outcome of this workshop will provide a milestone for teaching, learning, and research in nanotechnology. Thank you.
Thank you so very much, ma'am, for your motivational words. Your speech is always motivational. And today I echo whatever ma'am has said. We strongly believe that nanotechnology is there in every field of science. Thank you so much for being with us.
Thank you.
Okay, now, ladies and gentlemen, moving along. So this brings us to the end of the inaugural session. Now, let me invite my colleague and the co-coordinator of the event, Dr. Nidhi Chauhan, to present a vote of thanks for this inaugural session. Dr. Nidhi Chauhan.
Thank you, ma'am. A warm and cherished morning to Professor Sunita Ratan, ma'am, Professor Opisana sir, Dr. Ranu ma'am, Mittal sir, invited guests and students. It is my privilege to propose a vote of thanks to all dignitaries for their valuable presence and acknowledge the contribution of those who work hard to make this workshop successful. Firstly, my humble thanks to our Honorable Founder President Sir for giving us this opportunity to extend our research at global platform and giving his blessing to organize this nanotechnology workshop. He has always been an ideal for all of us. His generous nature and continuous motivation to achieve the target have been our key to success. Sir, we are truly blessed to have you as our mentor. Thank you so much, sir. Next, I would like to extend my sincere thanks to our respected Chancellor, sir, for his efforts towards our MIT University. His own ideas and elegance of explanation of everything, I will mention my deepest sense of appreciation. Thank you so much, sir. I heartily thanks our Honorable BC ma'am for encouraging us to conduct this workshop. I would like to inform you all that with her leadership, continuous motivation, and tremendous supports, MIT University is becoming the top research university across the globe. Her leadership and her passion as a researcher and teacher has been a constant source of inspiration to all of us. She has been a great asset to not just our university, but for the whole research community. Once again, a big thank to our BC Professor Dr. Balbindra Shukla ma'am. My special thanks to Silva Murthy sir, President of MIT Science, Technology and Innovation Foundation and Director General of MIT Directorate of Science and Innovation. He always motivates us to pursue the research for better advancement and implement the idea for practical use. With his leadership, MIT University has achieved many scientific awards, highly reputed fundings, fellowship, and top institute in patent registration. His contribution and guidance in this workshop is highly appreciated. I also appreciate Sunita Ratan ma'am, Director and Professor, MIT Institute of Applied Sciences, who gave us valuable insight in current scenario of the research. She is highly respected researcher and valuable asset for our MIT University. Her scientific experience and innovation idea have impacted scientific community. Her presence here today surely increased the importance of this workshop. Dr. Ratan, who has been with MIT since the early years and has contributed a lot to the various institutes. As the Director of Applied Sciences, she has always provided A&T with her valuable time and assistance. Thank you so much, ma'am. Now I extend my thanks to our respected Professor Opisana sir, Director A&T. Without his supervision, this workshop would not be possible. He is our mentor who continuously pushes us for better and innovative science. As he said earlier, nanotechnology is a next generation booming area with widespread application. During this 4-day workshop, you all will witness the role of nanotechnology in environment, solar energy, sensing technology, and medical science from expertise all over the India. In closing, I express my deepest gratitude to each and every one of you present here today. I have highly appreciate you for taking the time to be with us on this amazing journey for the next 4 days, and I hope you will find this 4 day filled with the wonder and scientific curiosity. Thank you all. Now, without any further delay, let's start today's session. I would like to invite Mittal sir and Rohit to coordinate the first session.
Dr. Nidhi,
Yes.
let's actually thank you so much for an extended and warm vote of thanks. Well, before we begin the technical session, as a tradition, we would like to play the national anthem. I will request each one of the participants and the panelists to kindly raise for the national anthem. Well, welcome once again. So now we will begin our technical session, and that will be coordinated by the main coordinator of the event, Dr. Jagjeevan Mittal, and one of our very enthusiastic PhD scholar, Mr. Rohit Sharma. Over to you.
Thank you.
Ranu, Dr. Mittal, just to add that there is a slightly change in the schedule. Professor Rajiv Prakash will be joining around 11 o'clock. So his talk will be in the second. And we requested Professor Shankar Ramji, who is from the IIT Kharagpur. So his talk will be first. And I am thankful to him that even in the short notice, he agreed to deliver the first talk. So welcome, sir. Welcome to our institute. And now our coordinator will be handle the session.
Thank you, Dr. Sinha. Thank you, Dr. Ranu, and thank you, Dr. Nidhi. Now we have 3 speakers today. So first is about Professor Shankar Ram. So Rohit, can you explain the detail? Rohit. Rohit.
So very warm good morning to all. Myself Rohit Sharma along with Dr. Jagjeevan Mittal going to coordinate this session. We have first eminent speaker with us, Professor S. Ram. Dr. S. Ram had received his MSc in physics and PhD in physics from Banaras Hindu University in 1978 and 1982 respectively. From 1982 to 87, he served as a research associate at IIT Kanpur in recognition to his contribution in developing varieties of advanced materials, innovative properties, and their technologies. He had received several prestigious awards in his credit, such as Alexander von Humboldt Fellowship, CNRS Fellowship, MIRS Medal in 2003. He served as a visiting scientist and professor at MC Master University, Canada, IIT Madras, and in Ulam University. At his regular service after a scientist at CSIR Metallurgy Laboratory and ML Jamshedpur, he had joined Material Science Center Indian at IIT Kharagpur as assistant professor in 1986. He has published several papers in peer-reviewed journals, 11 patents, 13 book chapters, supervised many PhD students MTech students and BTech students. He carried out 15 sponsored projects on nanomaterial, biomaterial, and application. His research interest includes developing different kind of glass ceramic alloys, magnetoceramics, intermetallic nanofluids, magneto-optic materials, and energy and high energy density magnetics, ferroics, superconductors, sensors, GMR, and many more. Professor S. Ram had served as the head Material Science Center, IIT Kharagpur during 2011 to 2014, the president of Material Science Section in 100th Indian Science Congress at Calcutta University in 2013. From 2013 to 2018, he had served as a chairman Bureau of Indian Standard, Delhi Government of India. At present, he is serving as editorial board of member of several international journals. At present, his world ranking is within top 0.5% of the discipline of research in material science and application. The title of his talk is Smart Nanostructure, Nanotechnology and Their Societal Impact. With this, I would like to welcome you, sir. Please confine your talk to in 45 to 50 minutes, followed by 10 to 15 minutes for question answer session. The platform is yours, sir. Please share your presentation with us, sir. Hello.
Hello.
Good morning, sir. Please share your presentation with us, sir.
Sir, welcome, sir. Welcome to our organization.
Sinha sir, namaskar.
So,
Yes.
yes.
Yes, sir.
Yes, sir. We can see, sir. Okay.
Good morning to everyone present in this workshop at MIT Institute of Technology. With your kind permission, let me convey my sincere thanks to Professor O.P. Sinha and his group for inviting me over here to share some of my experience on nanomaterials and their applications. This is a very interesting topic decided by Professor O.P. Sinha of this workshop, that is smart nanotechnology for societal applications. As it is pointed out rightly in their programs, this is a very fascinating and challenging issue nowadays, especially to maintain green environment, green source of energy. As I had pointed out in this at the bottom, I pointed out over here, the challenge starts from the course and engineering over here. And there are various materials used nowadays, synthesized in the laboratory in order to clean the water. And nowadays, there are several industries, for example, foods, textiles, cosmetics, leathers, papers, which are producing huge amount of toxic. And they are throwing it right away in the green water or natural water, and that is polluting the environment very heavily throughout the globe. For example, here you see that this is a river and water is highly dirty, polluted, and people are using it. So this water is polluting the total environment throughout the globe. And also there are very good industries which are producing different kinds of medicines, and that is also polluting this environment very heavily. Within last 2 years, you have seen this dangerous virus, COVID, and this is is spreading throughout the globe, especially because of the pollution of the control. So we need the pollution-free atmosphere throughout the globe. Especially we need to clean our nature in different ways. So I will try here to give some points, especially for the students at MTech level, PhD levels, and young researchers who are interested to work on this topic, especially smart nanostructures, what are small nanostructures, what is nanotechnology, and how that can be useful for our green society. So main purpose is to maintain a green nature and a green society. Green society means functional society. So we are polluting our green environment as well as our society. So in both sectors, nanotechnology thinking, philosophy can be very useful in this context. So this is my first talk, especially at this institute, Noida. So with your kind permission, I would like to dedicate this discussion to the group of MIT University, especially nanotechnology group. So I have given over here. So this dedication is going to organizers, faculty members, guests, students, and staffs who are attending this program at Institute of Nanotechnology, Noida. And as pointed out earlier, this is a very good program, especially to maintain a green environment. And thanks goes especially to Professor Sinha starting this activation, this program, especially at MIT University. So I will begin my talk from over here, that is smart nanostructures and their technology, nanotechnology especially we call nowadays, and what will be social impact for the development of nanostructure materials and their technology. So I request especially the young researchers to listen this talk very carefully, because every word is going to have certain meaning and that is not available in the literature. That's why sometimes I speak very hardly that our young generation is not interested to learn basic science especially. So unless until we understand basic science, it is not possible to synthesize smart nanomaterials, or it is not possible to develop their technology. So basic understanding of science is highly required. So here I say that any synthetic material or green creature grows in order to maintain the stability. And the second point comes immunity. So it is growing in a way that it is developing its own stability, immunity in certain applications, functionalities, and here is a term fugacity. Fugacity, and overall we need a material which is eco-friendly. We also need people to work in the society who are eco-friendly, means they are having eco-fertility. So it is not necessary that all materials which are smart for the application, they are eco-friendly. Some they are not eco-friendly. They are not having eco-fertilities, but they are very useful for certain applications. So both kinds of materials are necessary, but here we are interested in eco-friendly material, ecological material, ecological people. So these are possible to understand only when we are interested to learn the basic things, because I don't have time to explain everything over here. So I leave this point on you to understand what is meaning of stability of material or stability of a person, what is meaning of immunity of the material, and what are different kinds of functionality that we are developing in nanomaterial. then overall fugacity is important over here. Suppose a material or person is highly capable for certain function, but it is not necessary that he will function for particular application. So fugacity is required, and that is interest to work is required. For example, I point out that in Mahabharata, if you look, Bhishma was very powerful character, but somehow he was not functional to the society, to his group, because he cannot deviate from his own principle, from his own logic. It means his vivacity was zero. And on the other hand, Lord Krishna was highly functional to the society because he was having controlled fugacity. So this fugacity in material a person is required in order to give functionality. So these are some points, and here there is a strong correlation, or you can say inversal relation in science, technology, and society. So science and technology are highly related each other, and if you look seriously, they have direct impact on the society. So there is strong correlation between science, technology, and society. If you look around the nature throughout the globe, you can find that in nature we are having different kinds of creatures. We are developing in their own ways in order to maintain the ecology. So the God has created the nature in a way that it contains several varieties of creatures, and that are required in order to maintain the ecology, equilibrium system. For example, here I put one figure, it's missing here, relation. And a relation means mother and babies relation. And this, in terms of material science and science, we are calling electron-proton coupling. So electron-proton coupling means if you take any material, then a material is functioning in terms of certain application, especially optical properties, when there is electron-proton coupling. Electron-proton coupling means electron is bound in the lattice to the atom in a way that it cannot function independently. Whereas if you go to the conductor, superconductor, there is no electron-proton coupling. So electron is free, so it can conduct very easily without binding to the lattice around. So both electron-proton coupling and non-coupling are required for different kinds of material. So the kind of material we are discussing over here, especially photocatalysis, that require electron-proton coupling. Means electron is functioning under the control of the lattice. That is very basic science. There are vibrations. I am not going to that detail. So they function according to the binding. So here I request especially the young researcher to go to develop non-biodegradable materials, non-degradable materials. And in order to develop that, we need green synthesis. Green synthesis, what are green synthesis? That requires independent torque. And then we should avoid non-degradable polymers or plastic that are widely used throughout the world for different applications. These are very fascinating materials, but they are not degrading with time, and they're creating a lot of pollution, especially water. So I request especially the young people to somehow avoid the research on polymers and plastics and go to the green material, biocompatible materials using green synthesis. So you learn what are the green synthesis. And here I have pointed out that these materials may be solid, liquid, and lasers, and solid materials that are important nowadays, especially for the science and technology and nanomaterials, I have listed over here. So I think Professor Sinha will circulate this slide to the students. They can read this because I don't have time to discuss every point. And today, this workshop is especially devoted to photocatalysis to maintain the green nature. So I will go on this point, photocatalysis. So I will try to discuss this point especially. Other points are also equally important. And then liquid, normal fluid is important. And then liquid crystals are very important. Superfluid is important. And nowadays, especially after the research on nanotechnology, nanomaterials, two important disciplines are developing, nanofluids. So these are liquid-like materials in which solid particles are dispersed in a mobile liquid. These are called nanofluids. They are very energetic. They are used in several fuels, exchange of energy, and then nanocolloids. There is a minor difference between nanofluids and nanocolloids. Some of them are biological. They are very useful. And if you cool the liquid, super cool in the form of the glass, and then the activity, stability is enhanced, especially in the glass, and they become ecological in several cases. So this is very growing discipline. In photocatalysis, another application is spintronics, ferroic, magnetics. If you prepare it as a glass is a super cool liquid, and especially alloy oxide and chalcogenides are getting very high level of interest worldwide to develop such kind of material to maintain a green nature. And then in gas phase, this material or even a solid phase, especially optical materials, are very important at laser or maybe light emitter, especially in UV region. There are several light emitters, but no good light emitters are available in UV region, that is 200 to 400 nanometers. So worldwide, people are searching the emitters in UV region. But here I point out that basic understanding of research is missing in this field. Suppose you look even science journal, nature journal, book literature, people are not having the basic understanding of the concept. They write first line incorrect, that suppose rare earth are used as optical centers or transition metal ions are used as center. They say that the emission power is not high because of the low solubility of the rare earth ions. But they do not know that in optical emission lasers, we need deliberately low concentration only. At high concentration, there is no light emission concentration punching this. So this basic understanding required. For example, if you go to gas state argon analyzer, that is lasing only when concentration of argon ion is at ppm level. So for laser applications, light applications, emitters, we need very low level of optical centers, but people are saying that we need high levels. In high level, energy is lost. That is called concentration questioning. So the basic understanding is required. Basics, unless until we develop basic knowledge of science and technology, it is not possible to develop the technology. And especially our young people are bypassing all these points. They are thinking that it is not necessary to waste time to learn the basic things. And also teachers are missing. Teachers are not available who can teach with interest the basic things. So this is a big issue nowadays. So I start from here. That is, what is nanomaterial? I had asked Professor Sinha to speak on nanomaterial basic things, but he said that, no, sir, we know many things. So I avoided that point. So I'm not going to tell what is nanomaterial, but a few basic points. For example, what is nanomaterial? I am not going to tell, but basic points. Suppose you take a material of infinite size. What is infinite size? I am not going to tell. Suppose this, and reduce this size, then at a particular value, this is RC value, you can find that surface energy is starting adding to the structure. A material function on two types of energy. One is called volume display energy and other is surface energy. So in bulk material, there is no surface energy practically available. It is functioning only on the volume display energy. If you reduce the size of the material, then a certain size appears, and that size, the size at which the material appears to be functional in terms of the surface energy, it is called nanomaterial. And so at this point, surface energy starts adding in the material, and it continues up to a certain point, and after that it becomes amorphous. So this is RC value, capital R, and that will be small RC value. Above only that a material exists in certain crystal structure, polymer, that is nanomaterial, that is a material of surface energy. And I have demonstrated over here that you can understand by using a term specific surface energy of a particle, SI. So SI means specific surface energy of a particle means total surface energy per unit mass. So suppose you consider a mass particle, crystallite crystal of a spherical shape of radius r, then 4 pi r square multiplied by sigma surface energy density will be total surface energy of the particle, and then you divide by mass, that is volume multiplied by density rho, 4 upon 3 pi r cube multiplied by rho. Then common terms are cancelled and we are getting very simple relation, 3 sigma by rho. Sigma is the surface energy density of the material and rho is density and r is the radius, effective radius here we call. In spherical surface here exponent n is equal to 1 spherical, but in reality there is no any material in spherical shape, no crystal structure is in spherical shape, and we are synthesizing deliberately material in rod shape, thin plates and so on, then n is greater than 1 in non-spherical particle. Here if you see, if r tends to infinity, then this term becomes 0. This becomes term 0, and then we say this material of infinite size, that is bulk material, means a material of no surface energy, three-dimensional material. But if you reduce size, effective size, equivalent size of the material, then it is starting adding surface energy. This total energy is growing up the material up to a certain point, and this we are called SI energy state. These are the internal energy state of the material, energy state of the material. I mean to say that by reducing size of the material, we are adding energy of the material, means material is storing energy. So it is going to this stage. So this is a nanomaterial. A nanomaterial, in other words, it is a hard materials, which it is not functioning from the ground electronic state. It is functioning from the excited energy state, like our children. So basic physics that is available 50 years, 60 years ago, means bulk material that is not applied over here. A bulk material functions from the ground electronic state, whereas nanomaterial function from excited energy state, and that excited state energy is determined by the size, shape, and topology of the material, surface topology, and its interaction with the surrounding. But main component over here is this surface energy size over here. So it functions from this state. If you decrease the size further, then it is not able to tolerate the excess energy. So it is decomposed, it goes to amorphous state. So up to this value, I have given the point RC, that is called critical dimension of thermodynamic stability of a particle. So any creature, any material exists in a given structure only at a size above RC value. So this RC value is important. This is called critical dimension of thermodynamic stability. I need 1 hour to explain this, but as a layman, you understand that a material, nanomaterial exists only above RC value. R means capital, and this is RC value, small value. So between these, a nanomaterial functioning at high energy state, higher energy state than this value, according to the Schrödinger equation, SI is equal to E psi. So in this case, we are increasing the E value. we are also tuning this Hamilton function over here. This is operator. So here you see that in nanomaterial we are having two potential valve. So we are changing this value and but this Hamiltonian also. So that is another issue you can read from over here. And especially in this photocatalysis, we need a material biocompatible and especially high surface area. And that high surface area is possible by decreasing the size of the material as pointed out over here. Another way, by creating a cellular structure, porous structures. So in order to increase the surface energy, total surface energy per unit mass, it is required to create porous material over here. For example, in porous material, you increase this surface area around 3000 meter square per gram. So huge value is required, especially in photocatalysis and degrading the toxic material. And this kind of material can be achieved easily if you look around the nature. For example, here I have given mushroom. This is cellular structure, and if you work through this, you can synthesize several value added material, especially carbon, which are useful for this solar energy application, green energy. And here I have listed energy carriers. So I said that we are creating nanomaterials means hot energy material, and hot energy materials means this energy is distributed in the energy carriers. So these are energy carriers. In bulk material, we are having these energy carriers means electrons, hole, ponons. All these are available in bulk materials also. But if you reduce the size below certain value RC, that in nanomaterial, then lattice itself behave as a energy carriers, cluster behaves as a nanocrystal, particle itself behaving as this is. So nanomaterial itself behave as energy carriers. For example, when I was in class 6, 7, then we have studied a poem on Mahatma Gandhi. ऐसे अद्भुत थे सेनानी रण में खुद से लड़ते थे. मतलब महात्मा गांधी सोल्जर भी थे और कैप्टन थे, यानी दो रोल प्ले करते थे. जैसे झांसी की रानी को देखें आप, लक्ष्मीबाई, शी वाज सोल्जर directly in addition to the energy carriers. So energy size means as energy carrier. So it is two potential well material. Nanomaterial is having two well potential, and physics is not developed on this now. How two potential well functions? No physics is available. So we need to develop the physics. We need to develop basic understanding how energy carriers function in a potential well of the lattice, means nanoparticle. And in order to understand, especially our PhD student, that how surface energy start functioning. Suppose you take a bulk material, the surface energy is 0, three-dimensional material, suppose 200 nanometer cube, and reduce the size, then up to this level, if you go to 100 nanometer, then surface energy is 0 only, practically. If you go to 50 nanometer and divide into 60 parts, then you can find that only 2.4% atoms are sitting at the surface. So only surface volume is 2.4%. So this is not significant to function in terms of the energy carriers available. This is surface. And such a particle 50 nanometer is having million of atoms here, around 2 millions. So true nanomaterial is actually for photocatalysis and electronic application pumps. If you increase the fraction of the surface atom to 10 to 20%, and that is possible when reduce the size further, that is 10 to the raised power 5 atoms. Suppose you are creating a structure, crystal or a powder structure, and then the number of atoms is roughly 10 to the raised 5, then this is true nanomaterial. This is having hierarchical structure of the distribution of atoms in different energy levels. Schrödinger equation SI is equal to E psi as well as distribution of the charge carriers, energy carriers. So what are energy carriers are pointed out here, and what are the charge carriers we need to describe over here. So 2 nanomaterial appears only at a 20 to 30 or 40 nanometer size. This is important. And if you look this here, then this is core cell structure. Surface atoms are not having complete coordination with the surrounding. So they are available in different structures in terms of the interatomic distance, symmetry, and charge. So this is a core cell structure. And here you can find the number of the surface atoms at the surface is very small, maybe 1%, 2%, 5%, 10%. But they are having surface active properties, surface prone properties. So all properties in such materials are coming from the surface atoms only, surface carriers only, surface charges only. Core is also contributing, but its contribution may be 0.1% or 0.01%. So it is not significant. So nanomaterials, most of the properties are coming from the surface atoms, although their fraction is very small. So this understanding is required. This is called surface enhanced activity. Surface enhanced activity, they are the energy carriers. So here electric dipole moment is changing by huge amount, 1 order, 2 order, and also polarizability is changing if it is a non-polar material, and that gives especially surface enhanced Raman spectrum that is useful in photocatalysis biomaterials. So I mean to say that core cell material of this structure, that is 2 nanomaterial, is having surface enhanced properties of charge carriers or energy carriers. I will not go to this one because this is basic things. And if this is example here, you know that all creatures function on the basis of the solar energy. So they are exchanging energy from the sun. Means exchanging means they are taking energy and they are giving energy to the surrounding. Exchange of energy. So any creature function by exchanging energy with the surrounding. Ultimate is sun over here. I have given the example of a car over here. And this car, if you look here, it is giving example, realization how a core cell structure store energy. Means store energy to the cell. Suppose you are taking this car, and if you are in Canada, I was in Canada, and if you enter season, suppose outside temperature is -10 degrees centigrade, then inside temperature, especially in the night, it is -20, -30, -50 degrees centigrade. Means it stores cold energy. And same car in the day night, suppose outside temperature is 10 degrees centigrade, then inside temperature may be 20 degrees centigrade, 30 degrees centigrade. So this is a practical example how a core cell structure stores energy depending upon the availability of the energy in the surrounding temperature gradient. And here you see that these are all the creatures, and they live green if water is provided properly, even in summer, even in winter, even in rainy season, because they are very smart material to exchange energy from the surrounding as much as required. So these are nanostructure. If you go to the electron microscopy, you can find that all creatures are having cells at a nanometer scale. So they are functioning in a core cell structure here. This is another example here, you know this very well. This is a cellular structure A, and here this mother is transferring energy to this. This is hard cell. It is hard to believe that energy is transferring from this to this or this to this, but it is critical example. By this process, baby available inside this, it is growing. So the critical example that is a control energy transfer from the surrounding to this material. So this is required. This is very small energy transfer that this is bringing functionality in the nature development. So in nanomaterial, especially smart materials, we need this kind of exchange energy through electrons and holes. Here it is on photocatalysis. This example on photocatalysis. So I pointed out that in India and other countries, we are having a lot of industries, that is food industry, leather industries, paper industries, cosmetics, and then pharmaceutical industries and textile. They are producing huge toxic chemicals, and this is very huge number, that is 700,000 tons per year. And they are dumping this total poison into the green water, natural water, without any treatments. So they are polluting the nature very heavily, and they are dumping this into the river, and from the river it is polluting surface, it is polluting the groundwater, it is polluting this seawater, and it means it is polluting the total earth here, this. And this photocatalysis is a process in which we are using certain material that is called photocatalysis material, and this photocatalysis material is mixed in this material in very small amount at the ppm level or micro level or milliliter level, depending upon the absorption coefficient of the material and other parameters. And then in presence of solar energy, especially visible or near IR radiation, near infrared radiation, then in the presence of light, this material, that is photocatalysis, inducing electron and hole, and these electrons and hole comes and deposit at the surface of the charge carriers, photocatalysis, and the toxic material, and oxidize the toxic materials. So this electron hole pair is very, very important. So in certain materials, we are able to create electron hole pair very easily, but they are having very fast recombinations. Means as soon as they are, say, electron is separated from the hole, electron hole pairs recombine immediately at 10 to the raised power 8, 10 to the raised power 9, second state and nanosecond level. So that is not useful for photocatalysis. In order to have photolysis, we need to increase this lifetime. This lifetime should go to 10 to the raised power -3, -4, -5 second. Then it is functional. So we are synthesizing spot material. So there are several photocatalysis, but we need photocatalysis which is having long lifetime. Means electron hole carriers are staying for the reaction for significant period of time. So this is important. That's why we are developing new material, and this is possible by creating a core cell structure, because core cell structure is increasing this lifetime. This increasing the lifetime, and then after decomposing, we are getting the component which are ecological, mean not toxic this. And this discipline also leads to this dissociation of water, H2O. So why we are dissociating H2O, so producing hydrogen. That is very good fuel. So this discipline also include dissociation of water and carbon dioxide. Sorry, here O should be capital, otherwise it is representing cobalt. So this is carbon dioxide. Carbon dioxide is also a pollutant, and reduction is required over here. So by using the same method, we are reducing carbon dioxide. So this discipline deals with dissociation, degradation of the wastewater, as well as decomposition of H2O to produce hydrogen, and reduction of carbon dioxide and several toxics. And major toxics over here, dyes are there, and most of them are poison. And catalysts, usually we are using metals, but different kinds of reduction reaction, redox reaction especially. So photocatalysis require redox reaction. So here metal are very good example, but not in every cases. And nowadays worldwide, especially people are very fascinated to work on porous carbon. So porous carbon, sp2c, that is also graphene. That is very useful, but basic disadvantage that this is having only pi electrons. These are high energy electrons. So excited state first is available around 220 nanometer only, means UV region. So this is not so functional. So we need a doping of non-bonding electrons. You read what are non-bonding electrons. So pi electrons means that is bonding completely or directly. They are not non-bonding electrons. Non-bonding electrons are the electrons localized on the atoms. So they are having low energy. For example, nitrogen is having non-bonding, O is having chlorine, chlorine. So by doping these atoms means we are doping non-bonding electrons, and these non-bonding electrons are having energy in visible region are 400, 350 nanometer like this. I mean to say that by doping these kinds of materials, we are adding additional energy level between 300 to 500 nanometers, and these are inducing optical absorption of this material because this photocatalysis require absorption of the catalyst material at the surface, and also we need to increase absorption coefficient. Absorption, optical absorption A is equal to epsilon CL. So read what is A. Also people are not able to understand what is A. A can be varied, absorbance can be varied log I0 by I by a factor of 10 to the raised power 5 or 6 only. But I visit in several IITs and several discussion, people do not understand. They are working on optical material, but they do not understand what is A. They say that they can vary A by 10 to the raised power 20, 30 and so on. So several nonsense research is going on. So I request to understand the basic things. What is A? A is equal to epsilon CL. Epsilon is extension coefficient, optical activity. C is concentration. L is optical length of the material at which we are measuring the signal. And then these material oxides are very important. For example, TiO2 is very important, especially TiO2 coated with this material. And this is ferroic material, multi-ferroic material, magnetic material, spintronics. So, but this is also giving this material and several other oxides. And besides all these, I suggest you to switch over to green biogenics. Green biogenics means leave all these materials and search new material that are green biogenics. Nature, from the nature, we can derive several best material, and people have started working on this one, but not much research is going on. And for example, here you see that how much of efforts worldwide are going on development of such material. For example, we are publishing 20,000, 25,000 papers per year, especially at this level. So huge research is going on photocatalysis development discipline. For example, this is biocatalyst.
Sir,
This
please,
is
sir, please finish in 5 minutes.
5 minutes, okay.
Okay, thank you.
So this is a bioresource. From here you can synthesize several value-added materials. Here you see that this is having a fibers, and if you burn it or use some chemical, then you can synthesize porous carbon. High quality of porous carbon is available over here, and it is containing nitrogen and oxygen, and this is highly activated material. So whatever you are getting by sophisticated chemical methods, you can synthesize same material by very simple method without no any cost. And another point is that if you take this material, there is no need to produce carbon. You can use this material as such as a photocatalyst. This is already working as a photocatalyst. For example, nature is polluting this pollution itself by this process. In river water, we are not throwing carbon. It is having such kind of process, and several plants, they are cleaning this material automatically. So photocatalysis in nature is taking place automatically by green nature. So we have to think about the green nature to use as it is. So this is another example. Yeah, they have very good photocatalysis material, just a nectar of this material. So this is reducing several toxic material, and you can produce also silver and gold all by this method. And this is a spintronics. I will not go over here. These are certain example. Magnetic material, spintronic. This is very hard subject. So especially for the interest of the young researchers. So these are some materials. You read these, and especially this point, I point out this. I give you some time, especially the people who are working nanomaterial, they have polluted this discipline. For example, if you look at high quality journal books and this, they say that nanomaterials are rich in defects. This is nonsense statement. This is nonsense statement, but this is everywhere. It is not necessary that a nanomaterial is rich in defects. It depends upon the way you are preparing the material. Suppose you are preparing the material by milling, mechanical attrition, certainly you are distorting the material, distortion creating. But a material which is growing of its own by nature, there is no defect. For example, these are true example of the nanomaterial, nano creatures, there is no defect. And if you go to the layman who have not gone to this school, they say that defect doesn't survive in early structure of the materials. But scientists do not think, engineers do not think, doctors do not think, they are polluting, giving the nonsense statement. Especially some American giving the statement, we are taking it granted without thinking at all. So here say that a material grows at the expense of the defect, excess energy. So that is first law of thermodynamics, second law of thermodynamics. So we need to respect the basic things. We are not respecting. You can also listen this talk in your this workshop also. Several professors speak that nanomaterials are rich in defects. It is not necessary. It depends upon the way. For example, here I quote this. I will take only 2 minutes. For example, Einstein says that looking all these points, it appears that science is complicated, nanoscience is complicated, technology is complicated, understanding is complicated, but it is not so. It is very simple. To develop the knowledge is very simple. So he's saying that I do not need to know everything. And of course, it is not required to know everything. And it is not possible to know everything for a single person. And if a person is trying to know everything at a time, he is a mad person. So I just need to know what I need to know and where I can find it when I need this. This is important. So it is not necessary to know everything. I just need to know what I need to know and where I can find it when I need it. So our young researchers are working very hard. They are interested to know something, but they do not know that what they want to know. This is basic things. And this is not an Einstein statement. For example, Hans Bunsen has also said this one. Several poets, Indian philosophers said that राह चलने के पूर्व बटोही बाट की पहचान करो. मैथिली संस्कृत ने भी कहा है, लेकिन हमारे साइंटिस्ट लोग इसको उतनी वैल्यू नहीं देते. फॉर एग्जाम्पल यू टेक Vivekananda. If you think very seriously, he has pointed out all these points, so that also thinking of Vivekananda is nanotechnology. He is saying that fill the brain with high thinkings and high thoughts. Means living creature, high energy carrier seal. So we need to increase our power, manpowers like this. So I pointed out that this is green technology. And remember here, especially that a creature function at exchange of its energy with nature here. So in nanomaterials, we are increasing the enthalpy, we are increasing here, and we are increasing entropy, functionality. Entropy here. So nanomaterial is the material of high entropy, high fugacity. And these are conclusions I will not read. Maybe that student can read over here. So nanoparticle, nano creature nucleate and grow at expense of net surface energy, and that is written very widely in the literature. Any creature nucleate and grow at expense of net surface energy means defects. Means nature tries to exist in defect-free state, and that is polluted in our science. And I thanks all of you for listening this lecture very carefully. Of course, I need 2 hours or 3 hours to explain this only 10 or 15 slides. Maybe there's some next time I'm grasping something and sharing the views in our joint favors. And especially I thank to my students and co-researchers, including all of you. Thank you very much for your listen. And
Thank you for a wonderful talk. Now, Dr. Mittal, you can take the question.
Yes, one question. Thank you, Professor Shankaram. This is a nice presentation and excellent. You told us the many aspects of nanotechnology and for societal applications. So, first question is MD Akib Hassan. He asks that how we control the environmental pollution with the help of nanotechnology. Professor Ram?
hello, yes.
So first question is from MD Akib Hassan that how we can control the environmental pollution with the help of nanotechnology.
Okay. So I pointed out that in environment we are having several toxics, several poisons. So we need to destroy them when they are coming from the industry. So these are the chemical, not degrading, not decomposing of its own. So we are using some catalyst to decompose them. And these catalysts are smart material. For example, I said that porous carbon. And porous carbon, especially it is called activated porous carbon. And especially by doping non-bonding electrons, means low energy electrons, that is oxygen available, nitrogen available, chlorine available. And this is again not sufficient. Then we are reducing the surface energy of the particle, means we are using nanotechnology, chemical synthesis. So we are especially activating energy carrier to function very easily. Means we are increasing the number of energy carriers sitting at the surface through the surface energy. So we are creating porous structure and small size. So porous structure, small size, and non-bonding electron doping. It is a nanotechnology, especially to create smart materials which are degrading this toxic material over here. And especially this is also controlling the electron phonon coupling, means electron hole bonding. So this material in the presence of the light, especially visible light and near IR light, exciting electrons from the conduction band, or exciting electron from the valence band to the conduction band. This electron is separated from the hole, but they are coupled electron hole pairs, but they recombine very rapidly at the scale of 10 to the power 8, 10 to the power minus 9 seconds. So by creating electron phonon coupling that we didn't discuss over here, means surface energy level that are phonons or surface energy states that we are creating nanomaterial, they are increasing the lifetime of the electron phonon coupling. So nanotechnology is very skilled technique in order to create the material as well as control the dynamics of the energy carriers, especially electron phonon in photocatalysis example here. So here in nanotechnology, we reduce the size of the material, we activate surface energy, we activate surface topology, means we recreate atoms sitting at the surface in specific structures. They are having non-bonding electrons. So, and then we are creating porosity, and then we are creating coupling between electron and hole, so that they are having lifetime 10 to the power 5 and 10 to the power 4 millisecond. And this is the nanotechnology in terms of the photocatalysis activity, especially to maintain green nature, to control the pollution. To control the pollution means degrade the pollutants available in the nature. that is in river water, sea water, underground water or surface water, especially in industries. So I hope that I answer your question.
Okay. I hope the question, this who wrote the question, he got the answer for that. Any questions from the panelists?
Mittal sir, there is one more question I've sent you through WhatsApp. You can see. Meanwhile,
I'll read it now.
yes.
Another question by
Any-
Nadeem Paresh. Sir, he's asking about, please put some light on the advances on supercapacitors for electrode material.
Supercapacitors.
Yes, sir.
Supercapacitors, no?
Yes, sir. Electrode
Yes.
material for this.
Electrode material, lithium batteries and some this. So this material means same philosophy is applied also to increase magnetoelectrolytics or super catalyst material also. Means at the surface means core we are creating as large energy carriers as possible. That is supercapacitors.
Okay.
Okay, we'll get an answer by Nadeem. So I have a,
Supercapacitor. For example, this porous carbon, suppose you deposit a TiO2, that is supercapacitor. Even if you take gold particles, silver particles, and create at the surface this porous structure of carbon, that is a composite material, metal, carbon composite, or metal ceramic composite, cermets. These are supercapacitors. Also, you are taking certain polymers, and within the polymers, you are embedding metal particles. The metal is a conductor, it is not superconductor, supercapacitor. But at the surface, we are accumulating or storing the charged particles. So they are behaving as supercapacitor. For example, gold is a metal that is not a supercapacitor at all. But if you reduce the size of the gold at 5 nanometer, 10 nanometer, then valence electrons are not mobile anymore. They are localized at the surface of the particle. These are called surface plasmons. So they are having electric dipole moment. They are oscillating with the core of the particle. So they are having a charged particle stored at the surface of the particle. So this is supercapacitor. For example, if you look at polymer composite metals, for example, nickel is having the same properties, but nickel, silver, and gold is better supercapacitor, especially you are embedding in PBDF or polyvinyl alcohol, and several polymers are available. So supercapacitor. So supercapacitor is nothing but in certain metal particles or certain ceramic particles, we are storing charged particles, localized charge carriers at the surface in a core cell structure. So it is a core cell structure, composite structures, as pointed out. Even if we are having a single crystallite nanoparticle, it is a core cell structure, but density of charge carriers, density of state is not so high. So in order to increase the density of charge carrier at the surface, we are going to the two-phase model. Means one material is there and its surface we are adding another material. Maybe we can add third material also in order to capsulate the charges between two materials. Layer 1, layer 2 and layer 3. Maybe that two middle one is the charge and L1 is a supporting and third one is encapsulating. So L1, L2, L3. This is the best supercapacitor. This is core cell structure. Means it is network structure, localized structure of networks. Okay?
Yes.
thank you, sir. We have another question by the participant, Dharmendra Singh. Sir, please explain use of nanotechnology in day-to-day life.
Day-to-day life, we are using nanotechnology every day. For example, in food, suppose you are having good taste. Suppose you know how to prepare coffee. Coffee means coffee powder milk. But how tasty coffee is prepared, it depends upon the method you are using this. For example, I give you recipe that you prepare the coffee, it is not tasty, but some expert are very skilled to prepare tasty coffee. Material is same, component is same, but how you are mixing them, How we are mixing coffee through the milk particles, that is nanofluid. Nanofluid means how you are dispersing the nanoparticles in a nanofluid, that is important. So this is nanoscience. So in a food, whatever taste you are getting, suppose vegetables, that appears by development of small particles, nanoparticles in a medium, that is called nanofluid. For example, some fruits are very tasty. For example, you are having mango, and there are several varieties of mango. Some are tasty, some are not tasty. Suppose the same mango grown in Bengal, some is grown Banaras, and the taste is differing. The same varieties having different taste from places to places. So composition is same, only microstructure is changed. So this nanoscience is very important in the food, plants, and everywhere. In daily life, we are having use of this nanotechnology. So this understanding is very important. For example, in society, nanoparticles say that stay together, function together. In society, we stay together, we live together, we work together. But I say that we do not function together. We do not function together. Nanoscience is telling that live together, stay together, work together, and function together. That's why I added the term fugacity. Fugacity here. So a nanomaterial is a material which is having fugacity, and that is available in children. Suppose you take 1 year, 2 year, 3 year, 4 years, 10 years, baby, they are having functionality. They are working together. For example, if we take one rich person and one prince, their age is 5 years, and put them in a house, you can find that they start together, they start playing together. Why? Because a poor baby doesn't understand in which thermodynamic state it exists. Same thing, this rich prince guy, he doesn't understand in which thermodynamic state it exists. So they are playing together. But if you take the same friends after 10 years, 20 years, they cannot mix up at all. Because now they are able to understand which thermodynamic state they exist. You forget the example of Krishna and Sudama. They had maintained the friendship throughout with irrespective of their thermodynamic state. So nanomaterial is a material which is functioning without knowing in which thermodynamic state they exist. Are they smart enough to decide simultaneously from which thermodynamic state they should function? I said two contradictory things. I say a nanomaterial is innocent, not able to decide from which thermodynamic it should function. So it is functioning randomly, whatever thermodynamic state is available. Other statement is that a nanomaterial is too smart to decide simultaneously from which thermodynamic state it should function. So both properties available in nanomaterial. It is a long discussion. For example, you look up the statement of Rabindranath Tagore. He has written a statement, last child. लास्ट चाइल्ड मतलब एक बच्चा होता है, वो अपनी मम्मी के साथ मेले में जाता है, और मेले में जाता है तो उससे पूछता है मम्मी ये चाहिए, मम्मी ये चाहिए, मम्मी ये चाहिए। मम्मी बोलती है बेटा बाद में, बेटा बाद में, बाद में। कुछ देरी के बाद में बच्चा मम्मी से अलग हो जाता है, पुलिस वाले के पास जाते हैं, बच्चे से पूछते हैं बेटा ये ले लो, बेटा ले लो। मैंने जो पहले मांग रहा था उसी को दे रहे हैं, लेकिन वही बच्चा बोल रहा है कि हमको नहीं चाहिए। तो उस बच्चे को अब क्या चाहिए? यानी उसको सिर्फ उसकी मम्मी चाहिए। So same thing is available in nanomaterial. It is highly selective. It is highly selective depending upon the potential well available by the material. That's why I say that nanomaterial function under the umbrella of the coarser structure and potential well of the surface charge carriers. जैसे मम्मी है, बच्चे के सेंस में मम्मी जो है सुप्रीम पावर है, जो हम मांगेंगे वो दे देगा। लेकिन जब मम्मी से बिछुड़ जाएगा बच्चा तो उसको सिर्फ मम्मी चाहिए और कुछ नहीं चाहिए। So nanomaterial is very smart to understand from which thermodynamic state it should function, or it is too innocent not to decide from which thermodynamic state it should function. So it is functioning from randomly from whichever thermodynamics available in the surroundings. So it is a very big discussion requires. I need 3-4 hours especially to explain what is nanomaterial, because I did not describe what is nanomaterial. And what is nanomaterial, it is not available in the textbook. It is not available in review article. Of course, there are several courses running on several institutions. People are teaching this, but in my opinion, there is no soul. They are teaching, but there is no knowledge. So nowadays, we need knowledge-based education, especially to increase the interest of the young generation, young students, as Swami Vivekananda said, that we need to increase the interest of the students. We do not need to dump knowledge unnecessarily in the young student that you read this, read this, read this. They should read why. Logic is required. So good teachers are required and good students are required. Both, and their coordination is required. Thank you very much. Any question? Dharmender, I think I addressed your point. धर्मेंद्र सर सो गया क्या? Hello.
Sir, I think the audiences are not able to speak as of now, but I think you've explained very well.
Any other question?
Rohit, you're muted.
I have one.
मेरा address note कर लीजिए. If any question is there, they can write to me, telephone to me. I try to answer. I try to help the people who are interested to work on nanomaterial, especially in basic things.
Okay, I think no other question is there. So, Ranu madam, the Rajiv Prakashi is in waiting room. Can you enter him?
Yes, I have admitted all.
Okay. Professor Shankar Ram, we are highly thankful to you for taking time to present in this workshop. And I hope your talk will help all the young students and then our faculties for further understanding of nanotechnology and other aspects of this wonderful technology. Okay, thank you very much.
Thank you very much, sir.
Thank you. So,
moving ahead to the next talk, sir.
1 minute. I will ask Rajiv Prakashi if he is able to. He is waiting room.
Professor Prakash has joined. Professor
Yes,
Rajiv
okay.
Prakash has joined.
Okay. So Rohit, you can start with the Dr. Rajiv Prakash, Professor Rajiv Prakash. Okay.
Thank you.
Professor Shankaram, may I please ask you to
Shankaram, sir.
unshare your screen?
Just a minute. Thank you, Shankaram sir, for your really wonderful talk, for giving us such a deliberated idea about the nanomaterial, especially in terms of the thermodynamics. And I hope our student will get benefited how the small physics or the chemistry or the other materials can help us in the better understanding of the material. Thank you, sir.
Okay. Rohit.
Okay, sir. So thank you, Professor Esram, for giving an informative talk on nanotechnology and their societal application. Moving ahead, we have next eminent speaker is Professor Rajiv Prakash. Professor Rajiv Prakash received his MTech degree in Materials Technology from Indian Institute of Technology, Banaras Hindu University, and completed his PhD from Tata Institute of Fundamental Research, Bombay in 1999. Currently, he is a professor of material science and technology and dean at IIT BHU. Before joining IIT BHU, he served CSIR, IITR Lucknow as a scientist for 7 years. His area of research includes polymer and nanocomposites, organic electronics, sensor and electronic energy storage devices. He is having more than 200 publications in in peer-reviewed journals, having 22 patents to his credit, out of which 2 technologies has been transferred for commercialization. He has been recipient of Young Scientist Award from Council of Science and Technology, Young Engineer Award of India, and Material Research Society, Metal Award of India. He is the editorial board member of several national and international journals. He is a member of various national committees, including DST TIF AC for India Vision 2035, and MHRD Imprint, the program, member of Accelerator User Committee of Inter-University Accelerator Center, New Delhi, member of Defense Corridor Project of Government of India, and member of Advisory Committee for Technical Development Program of DST New Delhi. With this, I would like to invite you, sir, to finish your talk. Please compile your talk in 45 to 50 minutes, followed by 10 to 15 minutes for question answer session. Platform is yours, sir. Please share your presentation with us, sir.
Thank you very much. And let me share my screen. Is it visible to you?
Yes, sir. It is visible to us.
I am properly audible?
Yes, sir. You are audible.
So before I start, let me first apologies for rescheduling this talk. And there was some confusion, but I'm sorry. So for this rescheduling. But anyway, rescheduled in one way good, because the previous speakers, he might have introduced nanotechnology properly. So I will get opportunity to continue from what he left. I'm thankful to Professor Sinha for giving me this opportunity. So really thankful. And I'm also thankful to Amity for once again inviting me for this type of interaction programs and seminars. So as I know, the topic of seminar is smart nanotechnology for societal application. So let me start with this slide. The first one. Okay. Just my request, if the slides are not changing, so please let me know, because I have noticed that many times slides are not changing. So you just let me know. Otherwise, okay. So the next slide is visible to all of you?
Yes, sir.
Oh, great. So friends, okay, before I continue, may I know the audience, who is the audience, because this is the problem in online, you cannot see your audience. So who is the audience?
Sir, the audience are the graduate student, postgraduate student, research scholars, and some of the young faculty.
Oh, great. So this is very nice, and this is very good combination also. So I'm in most of the slides, I will try to address my young students. So graduate, undergraduate, and PG and PhD students. So friends, if you see this slide, I have tried to give you a glimpse of a nano, means size. And ant is the few millimeter to centimeter, and you go down bugs, and then go further down cell, and then you go further down the DNA, and in this way you will find the atoms arrangement. So this is the scale. So atoms are angstrom unit. In angstrom, the distance between atoms, few angstrom, molecules, few angstroms to nanometer, and then if you see your DNA is the nanometer scale. So the nanometer, you can visualize the size of a nanometer is the clusters of atoms, clusters of some molecules, like your DNA, are some chains, polymer chains, they are of the size of nano. So nano can be how we can see in nano in our science, that there is a cluster of atoms, are the colloidals, are the nanoparticles, are the nanocrystallites. These are the nano because of its size. So So we are saying that if they're the 50 units of the atoms or the molecules are coming together, the size will come of nano, which we are often seeing in a case of the clusters, or we can see in the case of the colloidal nanoparticles itself, the particle is the size of nano. Are the nanoparticles where the particle is of the size of nano, means size of the few nanometers. And nanocrystals, little difference from the particles and crystal that I will try to explain. When it is a crystalline nature, then the crystallites are called the nanocrystalline or nanocrystallites. And if it is not necessary as a crystallites, amorphous or the crystallite mixture, then altogether is a particle. So a particle can have the many small crystallites. So one particle is say of the 100 nanometer, then there may be the possibility of the 10 or 20 nanometer crystallites. So it's a combination of 3-4 domains. Is there any question or some conversation? I'm getting some background noise. Okay. Oh, this is online. Okay,
yes.
so the crystallites, so the in a one particle, there are the many crystallites are possible. So all these, because of the scale, is called nano. The question is coming, which is a bigger, that why we are concentrated on nano, why we are talking about nano. So though nano means what? Just not a size. Of course, you will say, if I have a ball, this ball size is say 5 centimeter. If I cut this ball, I will get the 2 balls, and we will introduce the surface area, the 2 surface area of this 2 halves of the ball. So in this way, if you cut in the 4, then you will again introduce some new surface area. And if you cut further and many pieces, then you are introducing some surface area. And this surface area introduction is from the same material, means the initial material was say 1 gram of material, 1 gram material having 1 ball, and this 1 gram material cut in 2 pieces, 500 milligram, 500 milligram, then cut 4 pieces, 250 milligram, 250 milligram. But the total material is the same 1 gram, but you are keep on increasing the area, the size, and the area because of the size. So the one argument is very good, that you may say that when you are going towards the nano, then the aspect ratio, that's the volume to the surface area ratio, this is changing drastically, and you are getting large surface area. Large surface area means the energy, the internal energy and versus the surface energy will change, and this may bring some differences. Agree. But there are something more than this. Then what is this? Let's go to particle and the wave nature of electron. If the electron is having a wave nature, then there must be some wavelength, some size where the electron is free. If we keep on decrease the size, just assume like this, you are in your classroom. Your classroom size is 100 feet by 100 feet. In your class, you are running here and there, everywhere. Then what I did, I reduce the size. Then what you will do? If I am reducing the size of your classroom, then the total area where you can run in your class will decrease, will reduce. And suppose I keep on reducing the size of your classroom, and I confined you in a small cabin where you have 1 table and 1 chair. You are confined. So now you cannot go here and there. Now you are localized. Your identity is very much now known. I can locate your position. Earlier, it was not possible because the classroom was big and it was difficult to locate your position. But now I can locate your position. You are confined. And this is called the quantum confinement. So when you are keep on reducing the size of a material of a particle. So you are trying to confine the free electrons. Those electrons which are delocalized, you are trying to confine them. And this confinement can be in a well form, in a wire, in a dot form, means in 1D confinement, 2D confinement, and 3D confinement. 1D confinement, how I can define the 1D confinement means the electron can move in two directions freely, but not in a one direction. So if it is a sheet, in a sheet, electron can move in a X and Y direction, but not in a Z direction. If it is a wire, electron cannot move in X and Y direction. It can only move in a Z direction. If it is a dot, is a spherical, then electron cannot move in any direction. It is completely confined. But the confinement in any one direction is causing you the effect of the quantum confinement. This effect I have tried to show here, but I'm sure that in your graduation or maybe in post-graduation, you have studied the localization of the confinement of the electrons, and you have derived the Schrodinger wave equation. So friends, this is the sheet. So we call the nano sheet, means the sheet thickness is nano, not the area of the sheet, XY direction is nano. When we are called the nano wire, means the diameter of the wire is nano, not the length of the wire is nano. When we are called the nano dot or the quantum dots, then all the three directions are the nano. Some example, some real example I have given, though it is cartoon. So the first one, the top one, is showing the a tube, and that called the carbon nanotube. Carbon nanotube is the graphitic sheet which is rolled. Then graphitic sheet rolled, and it is from the tubular form. First time giving this example because the first it was reported in 1990s. And Ijima, they reported this with one of our alma mater, Professor Ajian, who was working on this material. And they found very interesting morphology, very interesting structure of this material. And this is the tubular form where X and Y direction means this is the confined, and length is maybe in micron. So it is the tube or the wire-like situation. If you see the left-hand side bottom picture is the same sheet, the graphitic sheets, but they are not the buckled, they are not the curved, they are the open sheets, and they are the layered sheets. And this is called the graphite sheets. Are when it is the single sheet or the separated sheet, we call the graphene sheet. There's not much difference between the graphene sheet and the graphitic sheet. Is the matter of the only arrangement in the spacing. If we are making it isolated, we call the graphene sheet. If you see right hand side bottom picture is the nanoparticles. It's a spherical particle. Generally, we are producing many metal nanoparticles like gold nanoparticles, silver nanoparticles. So you people are also synthesizing or knowing about gold nanoparticles. So this is the confinement of the electrons in all the directions. This is the here in we have some real picture. And the real picture, how you can get the real picture of nanomaterials. So interesting. Let me take one more minute here. Again, I'm for UG, PG, and our PhD students. So as you know, what I can see is using the optical light. This wavelength is 400 to 750 nanometers, roughly. This wavelength I have seen. And based on this wavelength, we have developed some lenses. And lenses are magnifying images. So magnifications, we are using the number of the lenses, and we are making the more and more magnifications. Then we called it the optical microscope. Optical microscope, where the optical light is falling up the range of the 350 to 750 nanometer roughly. And this light we are seeing through lenses, and so magnified. but there is a resolution. Word is coming. Resolution means how small you can resolve. So how small you can resolve is a very simple. Our fingertips are few millimeters. So I can resolve few millimeter things if I resolve by touching from my finger. So some small spherical balls are lying on my table, and if I close my eye, I put my fingers there, I will realize few millimeters to sub-millimeters particles because I can feel from my finger. This is the resolution of my fingers. So what is a resolution from an optical light? Is a resolution of the wavelength. So up to the wavelength of a light, you can resolve. So roughly I'm saying, otherwise is a precisely it is a lambda by 2. So up to lambda resolution you can make. So resolution, as I said, 350 nanometer roughly of this you can resolve. But you need much better resolution. It is the theoretically you can resolve, but you are not able to resolve up to this using the optical microscope. So why optical microscope is the micron size microscope. It can see up to few micron, maybe sub-micron. But when you want to see further, then you have to reduce the wavelength of the electromagnetic radiation. And when you are reducing the wavelength of electromagnetic radiation, then you are reaching in the range of XRD, X-ray, where the diffraction is taking place because of the very small distance between the crystalline layers, are the electron wave. And both high energy electron wave or the X-rays, they are having very fine wavelength. So their resolution is going much below at 2 nano. And all these figures, all these images, what you are seeing is taken from the electron microscope. So what electron, but the colors you are seeing, they are the real color, they're the pseudo colors. In an optical microscope, because our eyes are seeing the optical range, so you can see the real color in optical microscope. But in electron microscope, these colors are the pseudo colors. So just to make some imaging contrast. So otherwise it is black and white. So bright field and dark field, that's all. And so what you are seeing these particles because of the electron waves, and so you can see the particles, you can see the nanotubes, nanowires, sheets, and in this way you can resolve the various morphologies. So what I was saying about the confinement. So, and the confinement means what is the difference coming in the confinement. So now you made the electron confined in a sheet, in a wire, or a spherical ball. So the continuous energy level earlier, if you see the extreme right hand side. So continuous level was there where I'm taking the typical example of a metal, say the gold. You were having the conduction band and the valence band, though I should not talk about in the metals conduction and the valence band separately, but let's see in the small particles there is a separation. It starts from continuous to discrete, and a valence band and conduction band is opening and with some band gap. And further, if you are reducing the size, then bands are now coming in a discrete in labels, and then what you are seeing some discrete energy levels. If you go extremely left hand side, there is a atom, the two atoms are coming, the two energy levels are there, bonding and anti-bonding. When the n atoms are coming, then there are the n number of the energy levels. So the number of atoms means the confinement. Confinement, when you are reducing the number of the atoms, reducing the number of the molecules or the size, and you are going to from right to left in this picture, then the band gap is changing. And if the band gap is changing, then the material is showing the different properties because of the change of band gap. And example I can take here, Nanomaterials, where the band gap is different in than in comparison to its bulk. In nanomaterials, the surface area is different in comparison to again in bulk. Then the interaction of various like light or heat or sound waves with your material in a bulk form and a nano form will change its behavior. So the light is interacting with bulk and light is interacting with nano will give the difference. And what difference is I have shown here, and this I have taken from internet. And this picture is showing very clear difference. Then a bulk gold is always golden, but a nano size gold material is not golden. So if you see the size different from 2.3 nanometer to 5.5 nanometers and change of color of gold nanoparticles from the bluish to reddish. So as you are moving toward the higher side, you see the color is changing. And this is the, again, this is why, because of the nano, the energy level, the band gap is different than the bulk. So bulk gold is always golden, but the nano gold is not the golden because of the change in band gap, which is depending on the number of the atoms, which is depending on the cluster size. And so based on this size, cluster size, that's changing the band gap and changing the color. So you are finding different colors in nanomaterial. As I said, how you can determine, how you can get the images are the size of a nanomaterial is by electron microscope. And at the top left-hand side picture is a typical picture of a electron microscope, and bottom picture is the atomic force microscope. I said, I gave example that I can touch from fingers and I can resolve the few millimeters or the sub-millimeters balls or the sub-millimeter size. So friends, this is the way how the AFM, atomic force microscopy, works. There you have a very fine, not like a finger, very, very small, but like a finger, you have a cantilever. Just it behaving like your finger. But the cantilever size is very, very small. It is in nano, and this nano cantilever size, when touching the material, then of course, if the bigger size my finger will resolve the millimeter or sub-millimeter sizes, and the cantilever, which is a nano, will resolve the nano, certainly the nano size. And so this is the atomic force mechanism, is the another way to resolve the nano size. So electron microscopy and same time the atomic force microscopy, atomic force techniques, where the 2-3 techniques are coming. And so these two are nowadays is a very good tool for us to see the nanomaterials, to realize the nanomaterials. So once we know how to see the nanomaterials, then let us try to make the nanomaterials. And you have seen in literature, then there are the two methods, the one top-down approach and the bottom-up approach are given there. So what is this? Let me quickly touch this. Then what is this? These two methods? Nothing. So in your day-to-day life, you have seen this way that how you can crush the bigger particle to smaller particles. So this is nothing. It is a top-to-down approach. So what you are crushing, you are breaking bigger particles in a smaller particles. Only thing is this: when you have to go to nano level, then you need some better way, better mechanism of crushing or breaking. So either you are using some high energy sonication, high energy ball mill. What is the high energy sonication and ball mill? Sonication, you know, the sonar waves you are sending, and high sonar waves are breaking nanoparticles present in solution. Ball mill is a very good technique where you have the jar, and in the jar you have the small hard ceramic balls, and along this jar and hard ceramic bars, you are putting your material there, and then you are putting the jar close and on a moving or rotating platform, and this platform is giving various type of rotations or vibrations. And in this way, what you will see that because of these vibrations or rotations, your materials will collide with the balls, these hard ceramic balls, and it will break in small pieces. And in this way, you will bring from a bigger size to a smaller size. And to bottom approach. And bottom up approach means you are synthesizing from a solution. You are taking a solution. Say, I'm taking a solution of the metal chloride, metal nitrates, and in a metal nitrates solution in a beaker, I'm adding hydroxide. So what happened? The metal hydroxide will precipitate. Metal hydroxide precipitate, I will take the metal hydroxide precipitates, dry it, and if I am controlling this precipitation, I will get the nanoclusters or the nano powders. So in this way, from top to bottom approach, you can find nanomaterial. A lot of attraction got this graphitic sheets. The graphitic sheets got attraction because the sheet structure, if you see the left-hand side, extreme left-hand side picture, then extreme left-hand side picture is the graphitic sheet, is the normal graphite material. If we open these sheets, then what we will do, we will get the individual sheet opened. And individual sheet opened means these sheets are nano sheets. Otherwise, when these sheets are together, it's a bulk material. So the 100 sheets or 200 sheets are together in a graphite is a bulk material. And just okay. And you are writing with a pencil. Pencil lead is a graphite, is a bulk material. Now what you are, when you are doing, when you are writing on a paper, what happened? From these graphitic sheets, some sheets are coming out because of this friction. When you are writing on a paper, your pencil is rubbing on paper. Your pencil is creating some friction over paper. And this friction is enough to take some of the sheets over the paper. And so what you are getting writing black color writing over the paper. It is nothing. It is the sheets over the paper. So these sheets can be easily exfoliated, means it can be easily separated. So by rubbing, by tape scotch or tape method, you can take the sheets out. And when you are taking one or few sheets out, it is nothing. It is a nano sheets, so-called the graphene. There is another way, by thermal exfoliation or by chemical exfoliation. You can exfoliate, means you insert some materials inside the sheet and make some reaction so that it is giving a type of explosion for these sheets, and sheets will open. These are wonderful forces. Those sheets can be opened very easily. You can see here in the picture some cartoon I have shown that how the people are opening the sheets. People are opening the sheets by insertion of some chemical inside the sheet and doing some chemical reaction, exothermic reaction, and by heat the sheets layers are open. And you can get the opened sheets as a graphitic sheets opened in a form of graphene, and the graphene is a single layer or the few layers which is the nanomaterial, typically nanomaterial. And then you can see the figure E down. So I have shown the solution of the nanomaterials. So it's a very stable, dispersed solution of the nanomaterials. Other way, as I said, by bottom-up approach, where some precursor you are taking, like as I said, the metal nitrates, metal chlorides, and you are making some precipitation. But very close to this rather than using the simple solution precipitation method, people, because I said that if you control the solution precipitation, then you will turn up with a nanomaterial. In order to control, there is a way we call the sol gel method, where we are forming a gelation from solution. Sol is converting in gelation. So sol is to gel, and from gel, we are making it a dry gel, and from dry gel, a lot of porosity and crushing and getting the very easily zero gel nanoparticles. So this is the method of the sol gel, creation of nanomaterial. By solution, as I said, by pressing, rubbing, a lot of techniques are there to synthesize. But the issue is now coming, societal application. So we got the nanomaterials, we know how to make the nanomaterials, we know how to characterize nanomaterial, but when we are coming to applications. So this seminar is saying societal application. Societal application means the nanomaterial in society. So how the nanomaterials can help us? There are many ways. Some very high-tech areas, certainly, no doubt. But in day-to-day, if you see how our ancestors, our purvas, they were also knowing how to use the nanomaterials. What is the bhasma in Ayurveda? It's nanomaterials. From thousands of years back, they were knowing the beauty of nano. Today, what we are doing during the COVID time, what we did, we tried to get a lot of kadhas, a lot of gargling solutions, which are not the chemical, which were the some Ayurvedic products having some metal oxides in a form of nano. And then these extracts we were keeping in throat to kill the bacteria, to kill the virus. Why? If we are having a good nano solution, this nano solution, the surface area will have a lot of dangling bond, lot of unsaturated bonds. So lot of energy. The surface area will have a lot of energy that can be enough to kill the wall of the virus. So if these viruses are coming in contact to the nanomaterial surface area, which is highly energetic, unstable, will try to get stabilized by giving the electron to virus or by taking the electron from virus. So in this way, what you will do, you will kill the cell of bacteria or the virus. So this is the way how the nanomaterials are used to kill the virus and bacteria. They are having the antimicrobial, antiviral properties. And in the COVID time, you have seen the lot of antiviral and antibacterial materials you used, not only for the eating or the gargling, but you used for the sanitization also, lot of nanomaterials. For the fabrics also, nowadays, a lot of fabrics are coming, which are the nanomaterials. Sorry, there was some disturbance, so I took a break. So how you can use these nanomaterials for antibacterial and antiviral properties, you have seen in our day-to-day life. But we'll come to some more applications. And before coming to some other applications where we are using, let me first pose this problem that for application, what we need. For application, we need these nanomaterials in processable form and in some form where we can use directly or indirectly. So one way is we make this nanomaterials coating, thin film or thick film. So how you will assemble these nanomaterials? So assembly of the nanomaterials, there is a one method that called with the physical methods where we are assembling nanomaterials through the some vapor deposition or the laser ablation, these techniques. I'm not talking about those because we have synthesized or we have developed the nanomaterials powder either by the bottom approach or the top to down approach or up. So we have now the nanomaterial in our hand. So there is a way you dissolve this, you suspend these materials and put one drop, we call the drop casting. So one drop, it will spread over the surface and the surface will coat with the nanomaterial called the drop casting method. Dip coating, you take your substrate, you dip in the solution of the nanomaterial or the colloidal or the
Hello? Hello, sir, are you there?
I think there is a connectivity problem, so just wait for some more minutes.
Okay, sir.
Okay, okay. Okay. So connecting? No. Okay, so okay.
Eva?
Yes, he's
Sir has come.
connected.
Sir has come. Sir
so
has
it
come.
put me out. Yeah. It put me out.
Yes, sir, it's fine now.
Yeah. Oh, please. So now it is visible.
Yeah.
Is
Yes,
it
sir.
visible?
Yes.
So by various techniques, we can coat these materials. So one technique which you know perhaps is one of the very simple technique. You are putting your material over the surface of water, and but the material should not be soluble in water. So the water insoluble material you are putting over the surface of the water, and by applying some forces, you are trying to bring these materials closer
Sir, you are muted. Sir, your sound is not coming.
Now is okay.
Yes, your sound. Yes, yes.
Actually, there is some problem. It is disconnecting me. But anyway, so in a language technique, how you are getting these nanoparticles assembly or nanoparticles film. So here some of the cartoons I have shown. The nanoparticles, they are the floating over water surface, and then you are pressurizing using some way, and then they are coming together, and then this assembly you are lifting over your substrate like this. So let me come quickly now. So these ways are there where you can get some good nanomaterials film, nanomaterials composite with the polymer films, and some of the films I have tried to show here. If you see the 2D material along with some polymer as a binder, because it will bind these nanomaterials together, and you are trying to coat over a surface, a substrate, for what? For making some device. So you see what we have done now. Some work directly related to our laboratory I'm trying to show here, and then application for various purposes, including the societal applications. So what we have done, we have taken the nanomaterials, 2D nanomaterials. It is the sheet of the MOS2. MOS2 sheets, along with some small amount of polymer, and you can see the polymer sheets as a picture A and B, and then the nanomaterials along with the polymers we have put over the water surface and lifted from the water surface. You see the picture C and D. So nanomaterials disperse in the polymeric films, which we can lift over a substrate.
Sir, excuse me, sir. We will be grateful if you can complete in 5 minutes. Okay.
And then you have when you got this, then you have utilization of your material for various purposes. So you can use this coated material film over some substrate for battery application, for supercapacitor application, for sensor application, for shielding application, and so on. So as a time constraint, let me come to one example of the sensors application. So how you can make these sensors? You have devices like a chemiresistive devices, means you have two electrodes. If you see left top picture, two electrodes, and in between the two electrodes there is the no connectivity, and you put the nanomaterials in between these two electrodes. So what it will do, it will give you the large surface area, and in between these two electrodes the nanomaterials are giving you a typical conductivity. And this conductivity, if you measure this conductivity in presence of some gases. So because of the interaction of the gases with these nanomaterials, the conductivity will change. And this change of conductivity can be measured as a change or the difference of the concentration of the gases. Example, we have a lot of fume sensors. So how it works? It is working, the material in a presence of fume is giving a difference in conductivity. And this difference in conductivity is measured as a indication that fume, as an alarm that fume is, or the smoke is present or not present. You can develop some better devices, and we call it the FET devices, field effect transistor devices, with the devices which are more sensitive. And you can modify these devices for the selective sensing. So what happened with these small differences which you can see in these devices, like a Schottky diode devices, FET devices. So the change of the current, you can see very significant difference in the change of current in a case of nano or in a case of the not nano materials. So here we have tried to show the differences when you have a very thin layer. So one layer is really nano material, 2-3 layers are the bulk, the 10 layers are above. So you can see the current voltage plot and the difference between the one layer and the multi layers. So the current difference is very much sensitive, and it is giving you the very sensitive result when you are using the nanomaterials using such devices. So based on this, the last slide I am trying to show, based on this, one can develop a gas sensor for any gas, like here it is shown for the ammonia. So what we did, we developed a FET, a field effect transistor. If you see the right hand side bottom, the configuration of FET, a field effect transistor, where the field effect transistor is nothing, where we have a insulator, where the semiconductor, over the semiconductor to source and drain, as you have seen the golden color line to source and drain. And the source and drain, the gap is very fine gap is there of the few micron to nano. And when you will put your material in between these channel, we call the channel material, then it will change the current of this device. So I versus V for blank, if you measure, as you can see, I have shown it with a black color. So I versus V graph in a black color is showing the blank reading. Now this device is exposed with ammonia, a typical concentration of ammonia, and then it came to red, means lot of loss in conductivity. And when we again flush it with air, it is going back green. So what it is showing? It is showing that this device can sense the presence of ammonia. So if you take the IV characteristics of no ammonia and in presence of ammonia, you will find the difference of the IV. So this current difference can be measured as for the quantification of ammonia gas. If you see the right hand side picture, the right hand side picture is showing that how the various concentration of ammonia can be sensed by the change of the current in the IDS and VDS plot. So friends, I tried to summarize and this work and nanomaterial work and nanomaterials, how we can use in sensor, and especially in gas sensor and gas sensors, where because of its large surface area, because of its reactivity, with easy reactivity, fast reactivity with the gases, it is easy to develop the gas sensors based on nanomaterial films. So I think I should stop here, and if some questions, please. Rohit, you can see if some questions are there.
Should I carry, Mithil sir?
Yes, you can carry. Yes.
Thank you, Professor Prakash, for such an enlightening talk on the nanotechnology and their societal applications. So there is a few questions in the chat box, like Chinmay Shukla is asking, sir, the lifetime and extreme activity of nanomaterials is a question in societal application. So how can one ensure a recyclable system? For example, the materials in sanitization application.
This is difficult for the recyclization of the materials in sanitization. This is not easy and not economical also. So why the people are trying to use low-cost material, cheaper material. So like zinc oxide, like alumina, like iron oxides. So the cheaper materials as in nanomaterials, or even the carbon nanocarbon materials. So
Hope you will get your answer, Chinmay. We have another question by Priya Mandal. Sir, like you discussed about soil gel technique, so can we use these for remediation of contaminated water or soil? Will the activity of nanoparticles can degrade over the time like the enzymes?
no. So they say, the soil gel technique is the different technique where you are synthesizing nanomaterials. So if you are using the nanomaterials in remediation, that is possible. People are doing because of the large surface area, you will get the benefit in the remediation. And in case of the nanomaterials in remediation, you will also get opportunity to recycle it, because there you are using as a column, or you are precipitating whole things along with the nanomaterials, and then you can get back your nanomaterials from there. So degradation of the nanomaterial is there, possibly is because of the side reactions, and because nanomaterials are highly reactive. So degradation is there. If there is a degradation, then there is no way. Means degradation means what? Degradation means the nanomaterial will solubilize. Or other way, the nanomaterial will clubbed, and nanomaterial will get the bulk size, bigger size.
If there is no question from the participant sides, I would like to ask the panelists if they have any question, they can ask directly to the Professor Prakash, sir. So we have another question from the participant sides between the nanoparticles and the nanoemulsion. Which would, sorry, this question is incomplete. I guess Anuradha, could you write it with more clarity?
So better see, it is the question like this: nano iron oxide is better or the nano gold is better? See, it is not the bulk gold and bulk iron. Certainly, if I ask a question, bulk gold is better or bulk iron, I will say gold. Then you will be richer if you have the 1 kg of gold. But it is not the question of the which one is better. It is the requirement. Where it is, what is the application? It's emulsion. It is having its own application. I did not get time. Otherwise, I was having some slides on the drugs. So if you want to apply a nano drug, so emulsion is always good. In wound healing, nowadays a lot of nanomaterials based wound healing drugs are available in market. They are the creams and they are the emulsion. And so just put it there, and the nanomaterials having some drug loaded, and it is much better in comparison to nanomaterials, pure nanomaterials, because sometimes pure nanomaterials may be toxic also. So it is the application.
So we have another question by Bhavna Bist. Thank you, sir, for the nice talk. I just want to ask about the current variation while use screen printing electrode. Is this an obvious thing, or what can we do to reduce the electrode to electro variation?
Bhavna, it seems that you are trying to develop the screen printed based sensors. And so you asked this question because you are getting the difference from one set of the electrode to another set of electrodes. And this will be always there. The screen printed based electrodes are not very much in use or reliable because of showing the large variation from one electrode to another electrode. So unless and until you are not having some perfect way of the printing of electrode, then it will be always there. And the reason why is the electrodes printing because of the porosity, because of the pores which are left behind after the screen printing. These are the causing the main area difference. And there is a word called the electroactive area, and the geometrical area. So this I am also observing that electroactive area is also significantly changing. Even you have the same geometrical area in screen printed electrode, but the electroactive areas are different. So this is the big challenge. And so I am not preferring a screen printed electrode for any use.
Okay, sir, thank you for presenting so nice informations and wonderful informations about nanotechnology. We are teaching nanotechnology, but we are also guided by your presentation for more informations about this. So thank you very much. And I think there are, if anybody has some more questions, he can directly contact you, or he can ask you about. We will inform, and then he can ask you about
Yeah,
that.
yes, please. Thank you very much. I have given my email also in chat box. So if anyone wants to send me email, so send me email. And I'm once again thankful to you and Amity family. And I hope that this program will be a very successful program. And once you are there, then certainly it will be a great program. Thank you.
Yes, we will invite you further, and we will collaborate with you. Yes.
Next time, physical meeting. And then
okay, good. Okay, thank you very much. So, okay, thank you. So, you can continue with.
Okay, sir. So thank you, Professor Prakash, for sharing such an enlightening talk on nanotechnology and their application on sensors and their basics. So with this, I would like to invite our next speaker.
Rohit, just a minute. Rohit, just a minute. Thank you, sir. Thank you, Rajiv Prakash, sir, for your time. And I am extremely sorry for the last minute miss. So thank you very much.
Should I continue, sir?
Yes.
So we have another eminent speaker is Dr. Praveen Chandra Pandey. Dr. Pandey is currently an associate professor in physics department at IIT BHU. He did his PhD in applied physics from IIT BHU in 2001. He has more than 16 years of teaching and research experience. During his research career, he has received several prestigious awards and fellowship. His research interest includes photonics, fiber optics, EM wave propagation in layered material using graded, meta, and dispersed material, semiconductors such as low-dimensional materials for photonic application, photonic crystal fibers, and nonlinear optics. He has given research guidance to several PhD and PG students. He has more than 100 publications to his credits and several citations. With this, the title of his talk is Luminescence Study of Some Dope Phosphors for White LED Applications. So please compile your talk in 45 to 15 minutes, followed by 10 to 15 minutes question answer section. Platform is yours. Please share your presentation with us.
Welcome, Pandeyji. Namaskar.
Namaskar, sir.
Nice to see you after such a long time. Please continue.
Thank you very much, Rohitji, for this nice introduction. And I'm very much grateful to be part of this workshop here with Amity family. Actually, my talk, I have requested for this talk on 30th of this month, but by somehow it will be preponed to 2 days. That's no issue. I will try to explain everything what I want to do here in this workshop. And I'm just going to share my PPT, the screen. Actually, is it visible?
Yes,
yes,
sir.
sir.
Yes, visible.
Okay, so let it come in presentation.
Yes, it is nice now. Yes,
It is nice. Okay.
Yes.
But I'm getting some. Okay, I just It is down. So, for today, I will prefer this there's some work which I have done here in recent past during 2018 to 2022. I'm going to discuss these work here in this workshop, in your workshop. So this is the work over phosphors. So we have worked over several kind of phosphors in the recent time, but I am focusing here only for molybdates here, for molybdates, which will be used in white LED application. So we are going to basically more intensely to discuss the luminescence study of some doped phosphors for white LED application. So the outline of my talk would be, so first of all, I will discuss some introductory part, introductions of and why phosphors are needed, what is the role of lanthanide materials, and other things we will discuss in that. Then we will go for some specific work which we have been done, and it will be published in here in recent time. So as you all know, but the slide is not changing. Yes, it has changed actually. Something is creating problem with this. Okay, so this screen is visible with some marks over that or anything else? Rohit, hello?
Yes, sir.
The slide is visible?
Yes, it is visible.
Yeah, okay. But some part of the slide is being hidden by some can say markings of June. But you should have to cope with it. So in the introduction part, first of all, we have to discuss this luminescence. So the luminescence is a basic element of any lighting events, or you can say any lighting devices. The luminescence, the emission of the light from certain material or organism after absorbing energy by the process of electric current, chemical reactions, mechanical force, or by absorbing the photon. So when we are giving some energy by any means to the materials, the proper materials, not everyone, to the proper material, then some luminescence would be possible. And this will be classified by excitation sources or by time durations also. In excitation sources, it could be electroluminescence, means if the source, excitation source is of electric field or electric effects will have been taken, so electroluminescence will be there. If the excitations will be done of the material by chemical reactions, then it will come in that chemical luminescence, and mechanoluminescence will also be there, through which we can obtain the dating of materials. So we can get that, in which some mechanical energy will be given to excite the atom source into the higher energy state, and then it will be come into that. So radioluminescence will also be there, where radiations, alpha, beta, gamma, and this type of radiations, if suppose it's falling over that, then it will be excited that. And thermoluminescence is the because of the heating and other things, through which actually we are getting some dating of materials by very easily by thermoluminescence, and most of that is the photoluminescence. And photoluminescence is here, when the photons will be when the material is being excited by some photons, and then there will be again release of the electrons from the excited state to the ground energy state. Then there will be release of another kind of photons, and that photons will be come into the radiations, visible radiations or ultraviolet infrared radiation. So this will be a kind of photoluminescence will be there. And so this will be of two kinds, it will be of fluorescence or phosphorescence. And you could get it some impressions that this luminescence would be possible. And we have very much in use in our day-to-day life with these bioluminescence in mushrooms, watches with tritium and radium could shine in darks. Also, thermoluminescence dating of ancient pots, so it could be obtained that, and mechanical luminescence will also be there. Fluorescence of LED materials will be a very proper things or good things which we are using in our daily life. Is this the LED bulbs, which reduce the energy consumptions, day-to-day energy consumptions tremendously in our households or in our country as well. So this is some aspects of luminescence, and because of that, fluorescence and phosphorescence is the one of the basic criteria of this photoluminescence. Slide is yes. So because this talk is based over the photoluminescence property, luminescence study of some phosphors. So that's why we should have to learn about this. We have to see what is fluorescence, what is phosphorescence. So from this Jablonski diagram, you can this has already been explained everything about the fluorescence, about the phosphorescence in that. So here, if we have some absorption by some energy being absorbed, photon absorptions will be there by some material. So it goes from ground energy state to the excited state, and this excited states are proposed singlet state, excited singlet state. So there will be some internal conversion will be there, and then it comes to the lowest level of the singlet level, and then it comes to the comes to the ground state, and that will be the fluorescence process will be completed, and we will got very quick response of the fluorescence. So in this process, the absorptions of the photons will be there, and molecular initially in the ground state goes to the excited state, and then after excited state, molecules then revert to the ground energy state, causing the emission of the photons with lower energy than the absorbed photon, and this will be basically take very small time in this process, and that is basically known as the fluorescence. And the second one is the phosphorescence, and in this process there will be some transitions from singlet state to triplet state, and then there will be conversion will be there, inter-system crossings will be there, and then we have inter-system conversion, and then from triplet state to the ground energy state, if system electrons excite molecules will come down, then they will radiate energy, and because they will have to go to inter-system crossings, then and in the triplet state it will take some more time to live there, and then the radiation time will be larger in comparison to the phosphorescence will be there. So in this process, the molecule is excited to the singlet state, and then goes to the intermediate excited triplet state, either by molecular collision or by inter-system collision. So the transitions from the singlet to triplet state involves spin reversal, and these things could be possible, and then you have we have obtained the phosphorescence from the particular material. Here, phosphorus, if suppose we are going to discuss some about the phosphor, so and its applications. So phosphor is a material that exhibits the phenomena of luminescence. Means when it absorbs some light, it goes to it has the ability to absorb the light, and then it has the ability to emit the radiations in a particular range of the light. So light range in the, suppose in the visible, so we are focusing for white LEDs. So this light radiations should become in the visible range actually. And so it emits lights when exposed from some typical radiation energy, and its applications, phosphorus applications are a lot of applications are there. So it has the indoor lighting, white LEDs. We have already used white LEDs several in our houses, and then the display devices, temperature sensing, optical thermometry is the one of the application of this type of material, phosphor materials with proper dopings. Then bioimaging and biomedicines, and then here smart anti counterfeiting applications. So these applications, these are the general applications where phosphors are basically be used. But we are focusing here in this talk is that for white LEDs. So here phosphors are of several kinds. You know, they are vanidates. They may have different kind of vanidates may also be possible. They have organic materials are also possible. Phosphates are there, silicates are there, and molybdates are also be there. So these molybdates have the molybdates has the term which could be written as XMOO4, where X can be of calcium, strontium, barium, zinc can be taken here. And some alkali metals can be doped here. Some rare earth metals can also be doped with it to enhance the property of luminescence property of that particular phosphor, molybdates, phosphor. So our main target is what? We have to improve the performance of white LEDs, which will be present here. And what is the limitations for this white LED, we will discuss later. And then we want to improve that luminescence which we are getting from the white LED in complete form of radiation in a complete sense. So that limitations will be solved out by using some doping materials like some lanthanides or by some transition metals. Here, so first of all, we have used strontium molybdates, and why we have used strontium molybdates here? Because this is a cost-effective synthesis which will be used urea-assisted auto-combustion method, which can be utilized here to get materials properly. Then tetragonal in its structure, crystal structure, space group will be there. Most of the thing, most important thing is here is its UV absorption. So they have the near UV absorption, and they will radiate in visible range actually. So near UV absorption, because of this oxygen to molybdate charge transfer in this group, and they have the blue emission, and the chemical and thermal stability will also be there for this type of strontium molybdate. So strontium molybdates, two words I am going to show here for strontium molybdate. One is for calcium molybdate also, to improve the luminescence property of that material. The main thing is here, light revolutions, if suppose we are to discuss that, we should have to discuss it first, but we can see it here. The light revolutions will come because of the LEDs, and they are white LEDs in that sense. And previously it was blue LEDs, then white LEDs are come. So light emitting diodes have transformed the lighting industry into a rapid growing business sector. It has because LEDs could be of indoor, outdoor lighting. It has the high power lighting also. Laser lighting will also be there by using the LEDs, plant lighting, near infrared lighting, and full spectrum lighting. So lot of things can be done by using the light of LEDs. Okay, so this light LEDs are one of the major things which revolutionize the science, actually, which revolutionize the which creates easiness in our day-to-day life, very very remarkably. So currently, solid-state lighting technology is presenting deeply into various market segments, which we have already discussed that these things could have the possibility for LEDs, and that LEDs would be made easily by phosphors with proper CRI indexing, color indexing actually. So here, the advantage of this, advantage of white LEDs over traditional light, we all know. We have not to go again for it, because it has the stable luminescence flux output, low power consumption. That is the basic thing, very important thing here, the low power consumption. High luminous efficiency is there, as well as short response time, environmental friendly, robust in nature. So all these things make LEDs very useful for our day-to-day life, for our life, and it making us because it is environmental friendly as well as low power consumption. So these two things provides the development of the any country that needs the development of any country. So this is a very big idea, very good things which have to be developed in this recent past. So first of all, we have to see what how the LEDs are working commercially. LEDs which are available here, white LEDs, how they are performing, what is the mechanism behind it? What is the mechanism behind? So commercially available LEDs, they have the build by fabricating indium gallium nitride as the blue LED chip, because indium gallium nitride here we have been this has been taken as the blue LED chip and coated with cerium with yellow phosphor over it. So a coating of a particular 5 phosphor will have over it, so that the blue color emission, and because of that blue color emission of that yellow color emission of the phosphor will also be obtained from there. So blue color and yellow color, both colors will be mixing together, and because of the mixing, they will provide somehow white LED, white color in that. So, but what are the limitations with it? They have lack of high color temperature, and because they have not the complete spectrum of that light which we needed it, and low color indexing causes because of the red deficiency. Because of red deficiency here, because we need blue, white, blue, yellow, and red to make the complete spectrum what we have in the white light. If you are making it in proper combinations, then we can get the complete white light as we have in the bright sunlight, you can say. So here, this is the mechanism of commercial available LEDs where blue lightning will obtain by gallium nitride by giving some potential here with it, and then over which, because of this blue light, they have been excited this phosphor, and then white LED is white, yellow, yellow radiations will be obtained. So here, this is the proper, this is the diagram we need, which is the eye effective diagram, which our eye actually required is this one. But because of we are using blue and yellow, then there will be some mismatch of this spectrum would be there. So we should have to keep that spectrum intact, or this complete spectrum to develop the complete spectrum. We require some additional element which gives the red light, so that this lacking of red color would be improved. Actually, lacking of red color could be solved by using that. So this is the simpler approach where the phosphor coated LEDs converted strategy. We have to use some material where this phosphor, which only giving us the yellow color. If suppose we have certainly some phosphor which gives yellow as well as red color, then this combination of blue, red, yellow will provide the complete spectrum, and so we could have the proper eye catching, you can say, human eye sensitive spectrums can be obtained properly. If any, if my wires or videos are gone in any disturbance, then please tell me anytime. So here is the need to develop the proper phosphors, red phosphors actually, to get complete human eye sensitive spectrum in our with the proper LED, with the LED which we are using. In commercial LED, there is some lacking of the red emissions. So we have to improve. We have to get that particular material, develop some particular material which improves the spectrum which is emitting from the LED, so that the human eye sensitivity will cover it properly. So red phosphor, such as some phosphors has been written here, have yielded warm white light. However, the large portion of the emission from the above mentioned red phosphors lie beyond the human eye long wavelength range, which imposes limitations of the use of these phosphor. So we have to use the proper material which emits the red colors properly with the excitation of near UV radiations, near UV or blue radiation. So the synthesis process of these phosphors requires high centering temperature. So we have to need some cost-effective mechanism as well in the synthesis process. In the synthesis process, cost-effective and environmental friendly too. Cost-effective in the sense that if it will be sintered in low temperature, or it require the low temperature, so we could have less power consumptions will be there in the fabrication of, in the developing of that particular material. So this will reduce a lot of energy consumption in making this type of material. So here, synthesis process are also is the important thing which could be managed, which could be taken in such a way that low cost will be done over that. So different approaches for obtaining that is, one of the approach is here we have to prepare, we have to make a proper we have to develop particular material and which have to paste over that gallium nitride film over that, and then from the blue light from the gallium nitride and other light which will be emitted from the over surface of that will combine together to give the complete eye sensitive spectrum from the white LED. So the main motive of that to obtain the complete human eye sensitive spectrum which we have from the sunlight easily. So we have to match the white light LED with the sun spectrum, white sun spectrum actually. So for that we have to develop that particular kind of material, and that could be done by using proper phosphors. And these phosphors are basically of we have taken a lot of phosphors for making this red emissions properly, but here we are going to discuss only molybdates for our for this purpose. So lanthanides are basically the important factor, important element which could be doped here with molybdates, which could give a proper emissions also in a particular range, which could be utilized to obtain the complete white light emission. So phosphor materials that exhibit the phenomena of luminescence, that is they emit the when exposed to the radiations with the ultraviolet light. Many molybdates, tungsten, vanadates, and phosphor compound have been studied by the researchers. Because of what? Because of they have the strong UV absorption, emission in the visible region, chemically and thermally stable and low cost synthesis will be there. So these things are basically for strontium molybdate. Will be true for strontium molybdates too, and some other kind of materials will also be taken, has already been discussed in different researchers. So let us see what we have obtained in some slides by using strontium molybdates as the host one, and then samarium doped strontium molybdate, and then its property, luminescence property enhancement by bismuth. Again, we have introducing including doping the bismuth in that, so enhance the property of that particular strontium molybdate with samarium dope. And this bismuth is taken as the co-dope. So synthesis is a series of strontium molybdate, SM3, and bismuth. So in this case, we have because for any discussions, for any proper understanding, we required a series, proper series of material to be discussed. Here, this workshop is for nanotechnology. Nanomaterials may also be included in there. Somehow we can prepare nanomaterials, but but some materials may also not be in the nanomaterials range, also be there, but they could give a proper lightning or luminescence property for it. So we have discussed, we have obtained, we have prepared by low cost synthesis method of this material. A series of material prepared phosphors were characterized by structural and optical characterization techniques like XRD, structural by XRD, by FTIR, and then optical characteristics by UV visible and photoluminescence study. Another studies will also be there here in these cases. So PL spectra for all samples reveals the enhancement in luminescence intensity for particular concentration. The energy transfer mechanism and possible connections between the result of the PL and structural study were discussed also here in this work. So strontium molybdates and samarium ion we have taken here. Why both these two? Because first of all, strontium molybdate phosphors have the structure, crystalline, silite type of structure, strong absorption in UV region, greenish blue emission. This is the important greenish blue emission of this host is there. First of all, that greenish blue emission of this host, which we are getting for YAG and cerium combinations with indium gallium nitride, there for commercially available white light. But here, this could easily give greenish blue emission with strong absorption in UV region. Another advantage including the chemical stability, thermal stability, and low cost synthesis. So they are, because of that, this strontium molybdate are very good candidate as a phosphor to provide luminescence property in terms of the LED. And samarium, we have used samarium as a doping here. So it has the reddish orange emission. It has basically well-known reddish orange emission. So emission, here we have greenish blue emission, reddish orange emissions are there. And then we have to shift it for some reddish emissions by using some bismuths and other thing. So we have to get some complete spectrum which we required from the white LED. So the advantage of samarium ion over other lanthanides, that the emission from samarium ion lies within the human eye wavelength limit, and it offers variations from 560 to 645 nanometer wavelength range. Reddish orange emissions of, so that's why samarium will be taken here because of its advantage over that. They have to emit radiations from reddish orange, and then we have combined together all these, then we can get complete white light. So this is auto combustion process for getting this materials for our study. So here precursors at the proper schematic ratios have been taken. Then they have mixed together, and then finally a solution was prepared in the hot air oven at 250 degrees Celsius for 2 hours, and has been put there, calcinated at 1000 degrees Celsius for 4 hours. So we have synthesized pure strontium molybdate, samarium dope 1%, 3%, 5%, 4%, 5% dope, samarium dope, strontium molybdate, and in 4% of samarium dope strontium molybdate, we have co-doped bismuth concentrations of 1, 2, and 3% for proper study, complete study of this. This work has been published in Journal of Rare in 2022. Actually. So correct. So different type of characteristics, because the time is limited. So I'm not going into every details of this characteristics characterizations, but you should have to know that when we are going to develop the material, we have to first properly check is this complete proper phase or not, and other things we have to check. And we have obtained the result refinement here, XRD plot of SRMO, SRMO4, and SRM, and with bismuth 2% as well. So these prepared phosphors have tetragonal crystal structures which we have to require lattice parameters and volume of that prepared phosphorus, which have been tabulated here, which we got that particular. The thing is here, if suppose we are going to see how the variations are being obtained, so the crystallinity of the phosphor is increased after bismuth co-doping, because we have some this strontium molybdate, with 1% samarium, 3% samarium, 4% samarium, then 5% samarium, and then in 4% samarium we have bismuth 1%, 2%, and 3% have been added. So here we can have with that calculation and WH plot, actually we can obtain that by when we are doping the bismuth co-doping, which indicates that the density of the grain boundary and the reduce the after bismuth co-doping. So the grain boundary are the source of the light absorption generated inside. So this all being given in this paper very elaborately, but and this crystallinity and other thing will be supposed crystallinity is improved actually by using the bismuth, which will favoring us for enhancement in the luminescence property of that. FTIR analysis has also been done for this SMO and and through which we could find that some groups, every groups are possible present here, but most of the things we have to discuss with is this the absorption study of this prepared samples. So in this absorption study, the bands of SMO centered at 260 nanometer is observed here at this bands will be observed, and this is because of the charge transfer band according to the charge transfer from oxygen to molybdates will be there, and then samarium doped samples show a small shift in the absorption peak towards the higher wavelength, which results in the decrease in the band gap. So there will be some, and this has also been calculated by the top plot as well. So bismuth 3+ co-doped samples, we have observed a peak around 303 nanometer, which increased the. So ultimately, we have obtained that it has the absorptions in near visible region. Because of that absorptions, we have to use that particular for the photoluminescence study, and photoluminescence citation and emission spectra of SRMO4 is shown here in this curve, and deconvolution will also be given here. But for a strontium molybdate ligand to metal transfer band is observed at 280 nanometer according to charge transfer from oxygen to molybdates. As expected here as well, the PLA broadband, the first peak around 280 nanometer correspond to ligand to metal charge transfer band group, and the second peak 293 corresponds for charge transfer band from oxygen to samarium. So transfer mechanisms would also be explained here. So we are not going into very detail of everything. I am going to show you some observations which we have been obtained here by doing that all the things. The samarium doped and bismuth and samarium co-doped strontium molybdate phosphorus were successfully prepared by the cost-effective solution combustion process. The XRD and FTIR analysis authenticate the phase purity and the vibrational mode of the prepared phosphor. The samarium doped phosphor emits reddish orange emissions centered at 645 nanometer due to this transition 4G5/2 to 6H9/2 transition of upon 404 nanometer excitation. Actually, in white LEDs, 404 nanometer excitation is very, very essential, important thing because of the. So we have excited this at 404 nanometer of excitation. This study reveals the emission of the intensity of samarium and strontium molybdate, which can be further increased by co-doping. Ultimately, the PL emission is increased. This is the important. The PL emission is increased up to 1.5 times when excited with 303 nanometer compared with the phosphorus with 304 nanometer. So this increase is due to the energy transfer from 3p1 level to level of bismuth ion to the energy level of samarium ions will also be possible. So these things gives, because in phosphorus, in energy, this charge transfer, energy transfers, these things have to be studied for getting the proper development of the material. Here the CIE diagram of this will have been given here, and it will be improved when we have the 2% of the bismuth ion because of the improvement of the crystallinity will be there. So other thing is here, we are certain that the suitable bismuth doping, samarium, co-dope, strontium molybdates, phosphorus may be a suitable candidate in the form of the cost-effective and efficient rate phosphorus for white LEDs application. So this is the one of the work which we have been which have done here in the recent past, through which we, by using the bismuth and by using strontium molybdates and samarium, we can obtain the efficient rate phosphorus for white LEDs application. Other things we can have to also to improve it by, because in material science or in this development of the materials for any concept, some proper dopings, proper co-dopings are very, very important things to get the required and
Sir, can you complete in just 2-3 minutes? Next 2-3 minutes.
Okay. So I'm going to only highlight the work which have been done,
No
and how this will be useful for white LEDs application, because the works are very similar and we have to get that because of different kind of dopings and other things to improve the luminescence, steady luminescence property of the properly strontium molybdates, and one of the work is for calcium molybdates too. So in this work, the phosphors are synthesized by lucrative urea-assisted solution combustion process, and structure analysis of strontium molybdates with 4% of samarium, which we have already discussed, that this will give the proper intense peak for this 4% of samarium. Zinc will be added here for iron for promoting the crystallite size growth. So doping of samarium decreases the band gap, which is supported by increasing the watch energy and other things. And here enhancement in the, because of when we are using the zinc at the place of bismuth, the enhancement is very tremendous. We have obtained enhancement in emission intensity by 87% after 1% zinc co-doping in the samarium of that. So this is one of the work which have been published in Journal of Luminescence here right now. In this work, one additional things we have been done here. It's for thermal PL, photoluminescence analysis of that. Actually, thermal stability is also be very important for white light application, because if we are using white light, if we are using LEDs for two things, if we are using in a in high temperature environment, as well as we are using for a very longer duration of time. So here, with the temperature, how the performance of the LED is decreasing or changing, we have to get some impressions about using temperature dependent photoluminescence. So this will also give a very enthusiastic result actually. Its stability, thermal stability is very good when we are using zinc in place of the bismuth with strontium molybdenate and some so temperature dependent PL analysis reveals that PL emission decay by 31% at 423 Kelvin. 423 means Kelvin. So the thermal activation energy was calculated, and this is 0.17. That would be very much in required range, good in required range, and so it will be improved. So the other work here is the calcium molybdenate with EU will be there. So this is also by using the manganese Mn as a co-doping with that, and this also provides a very proper result. So this also gives the building of very low cost rate emitting phosphors for white light LEDs here. In that case of when we use the calcium molybdenate in place of the strontium molybdenate. So these are some works over the molybdates. They are maybe their sizes are not in nano range, but slightly more than that nano range. But also they will be useful for very much required scenario actually nowadays, which we required lightning, and proper lightning actually will be done by using this type of material. So thank you very much to all of you, and
Thank you.
I stop here.
Thank you, Praveen. Really wonderful talk, and your expertise is also matching with me. Although, if you recall, we are in the BHU in the PC Srivastava lab.
Oh yeah. Yes.
You are with the, I think, Amrish, if I am right.
No, I am senior of Amrish actually.
Yes.
So with Pandey and other.
Yeah. Yes. I recall because you are quite frequently visiting our labs.
Yeah, so, definitely. Because I'm doing. I was done a project with Professor PC Srivastava sir. No?
Yes. I still remember. So basically, see, apart from the rare earth material, people are also trying to use the metal oxide for the luminescence.
Yeah, definitely. We have also proposed for rare earth free phosphor materials for lightning also. But that would be good because rare earth are very costly, as well as we have to dependent over the China, Australia. So if rare earth free phosphors are there, then it will be very good for us as well.
Yes, because our group is also working with this LED, and already if you see last few publications,
So you people are also doing very great. Well, we have just started in 18 actually, and we have done 13-14 papers.
Any specific region you are targeting manganese 2+ or the 3+ for the this luminescence property?
For here, okay. So manganese in calcium molybdenate, na?
No, yes. No, I am talking about the manganese. Mn. You were using Mn 2+.
Yes, Mn. Actually, we are trying to get some proper luminescence in different range actually, and with some proper intensity of luminescence too, a good intensity of luminescence. So transition metals are one of the materials which should have to be to give the some transitions in the range of individual range actually. So that's why we have to use that, and that transition metals are attached to cooled properly with known phosphors actually. That is also one of the basic things through which.
Okay. So further question from the audience, if any. Rohit, Dr. Mittal.
Yes, there is no questions. If you anybody wants to ask the question, please can raise hands if you have any questions. There are no questions.
Hello. So can I
Yes.
ask one question?
Yes, you
Sir,
can.
is there any 2D material that you suggest for white light LED application?
2D materials actually.
That is trending for white light LED.
Actually, I have not done any work over these 2D materials, and right now I could not recall that particular material. I will search and then I will discuss it. Okay.
Thank you so much, sir.
I have one question. Now the quantum dots, they are very much working for people are using them. So how you found there is like some comparison between these materials and quantum dots?
Actually, we have process of making of the quantum dots is different in comparison to these materials actually, and they have because we have to go for low cost synthesis material method as well, and that would be useful and properly prepared material be fine for us. So we could not go for quantum dots actually. But nanos and quantum dot have certainly some more applications in lightning as well as in different applications too. People are also doing it there. But we have not gone into that.
Okay, thank you, sir. You enlightened us about the luminescence properties of these materials. It is excellent presentation, and then I hope all the audience and then students they got enough knowledge about them, and then maybe they will work on the future. Okay, thank you very much.
Thank you very much, sir, for providing the opportunity to discuss our some work here with you people.
Yes, we
Parveen,
are
I
also.
will,
Yes.
Parveen, I will meet you sometime when I am visiting BHU. Although I am in touch with Anchal quite frequently,
Yes.
Anchal and
Yeah. Anjal is there, and Srivastava ji also is there. Sanjay Srivastava is there.
Yes.
They are also doing some work over the phosphorus and this type of materials.
Of course, we will collaborate
I
with you.
request you.
सिन्हा सर, आपके पेपर्स भी हम लोग देखते रहते हैं, बहुत सारे अच्छे पेपर्स आपके भी आ रहे हैं.
Thank you, Parveen. And I request you if you can just send me a hi because I don't have your number, but in email I must.
Definitely. Definitely, I will send you.
Sure.
Thank you.
Thank you
very
Parveen.
much.
Thank you.
Thank you. Okay, audience, thank you very much. This is the end of our first half of our this workshop. So we will meet at 2 o'clock, sharp 2 o'clock. So please join at that time. Okay. Okay.
रोहित जैसा एक पेन ड्राइव लेके इधर आजा फटाफट.
Okay, sure, sir.
Okay.
Post-lunch technical session of day one. We had a very fruitful pre-lunch session. All the speakers delivered their talks and audiences really enjoyed their talks. So I hope with the same zeal, everybody is going to attend the post-lunch session as well. So in this session, we have three eminent speakers lined up, followed by three of our young institutional achievers. So today's coordinator of this session is myself, Dr. Ranu Nayak, and Ms. Pooja Bhattacharya, a PhD scholar from our institute. So over to you, Pooja.
Thank you, ma'am. Good afternoon, everyone. Our first talk of the afternoon session will be by Dr. Rohit Ranganathan Gadam. Dr. Rohit Ranganathan Gadam is presently an assistant professor in the Department of Chemical Engineering at the Indian Institute of Science, Education and Research, Bhopal, India. Dr. Gadam pursued his PhD under Professor George Zhao at the University of Queensland on alkali ion batteries. He was awarded the International Postgraduate Research Scholarship and EQ Centennial Scholarship for his PhD. He also briefly pursued his research as a visiting scholar at Washington University in St. Louis, and pursued his master dissertation at CSIR Indian Institute of Chemical Technology. He is a recipient of prestigious Humboldt Fellowship to pursue his research in the field of energy storage at the Technical University of Munich, Germany. Dr. Gadam has several publications in reputed journals, a couple of book chapters, conference presentations in the field of energy storage and material chemistry. He has also grabbed few awards internationally recognizing his research outputs. His current research focuses on various aspects of advanced energy storage materials. Today, he will deliver his valuable insights on energy storage technologies beyond lithium-ion batteries. On this note, please welcome Dr. Rohit Ranganathan Gadam to this platform. The stage is all yours, sir. You have 45 minutes to conclude your talk, and after that 10 to 15 minutes of question answer. The stage is all yours, sir. Please share your slides.
Sure.
Welcome, Rohit. Welcome, Dr. Rohit Gadam.
Thank you, ma'am. How are you?
I'm so happy to see you.
Likewise, ma'am. So many thanks for the nice introduction. Also, I would like to share that I was a student of the same institute. Yeah.
Yes, that makes us feel so proud that you were our one of our bright star alumni.
Ma'am, am I visible actually?
Yes, you are visible and you're
Share my screen.
You have to share your screen.
Just a moment. So now, is the screen visible now? Hello?
Yes, it's visible. You can start.
Okay, yeah. Okay, thank you for having me here to present on the energy storage. So this is basically my research since my PhD, where I started to work on alkali ion batteries. And today, you know that we are moving towards more environmentally friendly technologies, which has lower carbon footprint, and we are also looking for having zero carbon emission by 2070. That's a very ambitious plan, and I think energy storage technology play a very important role here. So energy is a global problem, because energy plays a major role in global economics and global politics. Yeah, and with the growing population, growing technological advancements, you already know that the energy requirement grows a lot. So at present, most of our energy requirement, energy generation, is through fossil fuel means, which is a depleting resource. Yeah. So we have to move towards more renewable energy, and it's a more remarkable problem for India because we have a very good population, in their 30s now, and we have a lot of caliber. India is actually in the forefront of huge economic growth, and this can only be accelerated with proper energy generation and consumption. And we see that energy consumption in India is going to increase by at least 129% in the coming years. Yeah. However, these emissions, if you see the industrial emissions and the vehicular emissions put together, leads to a very undesirable impact. The air quality is very much reduced. Either it's very hazardous, very unhealthy, and a lot of diseases can be caused due to this air pollution. Yeah, it can also trigger oncogenes. You can get cancer because of this, because of carbon dust that's floating around, because of other pollutants like sulfur dioxide or nitrogen dioxide. So this is something we need to think about. And one way to curb these air pollution through vehicular emission is that we switch to electric vehicles. So electric vehicles seems to be a very promising thing these days, but we have to think of another thing. For example, if you take a simple car which runs through petrol or diesel, a Carnot engine based vehicle, yeah, as soon as you pour petrol, it starts to run. Yeah, but it's not the same with battery. You have to charge the battery, it takes time. And it's not that you can charge your battery very fast, because if you charge your battery very quickly, you lose the cycling stability. You lose the cycle life. You have to have a moderation, and you can't have, you can't discharge it completely. You have to maintain some depth of discharge. So these are some petrol-based vehicles. If you see, that tank that fills in the petrol, yeah, is very cheap, like whether it's made of stainless steel or aluminum. But the petrol, which is the fuel that runs the car, petrol or diesel, whatever may be, it is costly. But it is the other way around with battery. The battery is something that stores electricity, right? So battery is the tank. Electricity is the fuel. So the tank is costly, but the fuel is cheap. So now our motivation would be to somehow reduce the cost of this tank that stores electricity. So another thing, if you see the difference in vehicles, is that for a Carnot engine based vehicle that use petrol, if you see 1 kilogram of petrol gives you about 12,500 watt hour. So the energy density is 12,500 watt hour. To give you an idea what this is, what this watt hour is, if you think of the electric bill that you get, yeah, 1 unit of current is nothing but 1 kilowatt hour. Yeah, so you burn 100 watts of bulb, 100 watts of bulb for 1 hour, then that gives you 1 kilowatt hour. So this is what it is. And 1 kilowatt hour of that is 1 unit is just 5 rupees or 6, depending on where you are in India, but it's not that costly. So, and how much whatever you're able to store per kilogram is very important measure. How much whatever you store per kilogram or per liter. So volumetric or gravimetric energy density, this is what we call. And this becomes very essential when you talk about batteries, yeah, because as I already told you, it's 12,500 watt hour per kilogram when you use petrol, yeah. But when you use the recent ones, the cars, yeah, the cars, for the cars, for the electric vehicles, the battery that you use for today just gives 350 watt hour per kilogram. It has come a long way from 80 watt hour per kilogram to 350, but still it's 10 times lesser than what the petrol gives you, right? So which means you're going to increase the weight of the vehicle. So we have to keep this in mind as well. For example, if you consider a Tata Nexon based vehicle, the normal petrol-based version or the diesel-based version is just 10 lakhs, but the electric vehicle is around 18 lakhs. So which means they say that you give upfront cost for the battery, but as you keep charging and discharging the battery, it will lose its capacity. So also you don't have all the charging points available. So it's a bit long way to go, but rest assured that in the coming decade, we will not be having much of Carnot engine based vehicles. Rather, most of it will be replaced by electric vehicles. And not able, yeah. So this is for electric vehicle thing, yeah. But also you could also use batteries for grid level storage. So you see, so for grid level storage, people have already been working on energy generation technologies like solar and wind, but we know that these are very intermittent. So which means sometimes you have more generations and less consumption, and sometimes you have more consumption and less generation of electricity. So which means we need to buffer these changes using some kind of storage technology. Here also you will be having a electrochemical technology is very promising. So why do we need to use batteries in the first place? We found that we have these problems, but why batteries? So one thing is you can make it cost effective. It's a compact storage technology. It's pollution-free operation. So when you extract energy from batteries, it's not going to generate any pollution. Yeah, and good efficiency and good shelf and cycle life. And lithium-ion battery has been one of the most promising technology, and which has received the research on lithium ion batteries have got Professor Goodenough, Professor Whittingham, and Yoshino Nobel Prize for their seminal contributions towards this technology. Yeah? And if you see the basic operation of the battery, you have a cathode, you have an anode, you have a separator, and you have a electrolyte. Yeah, the ion shuttle gets inserted or deinserted between the cathode and anode during the charge or discharge. And in general, organic electrolytes are used. So probably they would be using lithium hexafluorophosphate as the salt, and with some organic ester-based electrolyte, cyclic esters and linear ester-based, a combination of these electrolytes, because these electrolytes give you a larger stability window. Otherwise, if you're going to use aqueous electrolyte, the problem would be that you just get a voltage window of 1.23 volts. So you don't want that. You want to, scan the whole voltage. You want to get the total output from whatever anode or cathode you're using. So this organic electrolytes are in a way, helpful for us in case of lithium-ion batteries. And the most commonly used cathode materials are lithium cobalt oxide, lithium manganese oxide, yeah, and NMP-based cathodes. And the most promising anode to date is graphite. And graphite gives a very good capacity of 372 milliampere per gram. Yeah, that's the specific capacity. And it has many advantages over the previous battery systems, and this doesn't have much of self-discharge, these lithium batteries, and it's a very stable system that has been studied for more than 2 or 3 decades. Yeah, but it does have some problems associated, at least in the Indian perspective. You can see that where the lithium resources are located, it's not in India. Yeah, so mostly in Bolivia, Argentina, Chile, United States, Australia, a little bit in Germany. So India has not much lithium precursors, which means we have to depend on other countries for procuring these materials. And these days, the situation is not very stable. The geopolitics plays a major role as well. So we cannot depend on resources that is not available with us. Rather, we have to look for technologies that we can indigenously develop. Yeah. Now, India is importing actually lithium precursors from Australia. So majority of our lithium precursors come from Australia. And another problem is you can see the thermal runaway with these battery systems, where the recent Samsung mobiles which caught fire, or even the Tesla cars, even the buses the Ola scooters very recently. So the thermal management is something we need to think about, because the batteries does catch fire and somehow we have to control it. Of course, we are able to control this in petrol or diesel. Even they are also inflammable. But somehow the technological advancement needs to there for better thermal management in batteries. So now, as I told you, because the precursors of lithium material is very much isolated, we don't have its rare material, which makes it very expensive in the long run to get these batteries into market. You can see the difference in the price range already between electric vehicle and the Carnot engine based vehicles. So that is something we need to look into. We have to reduce the cost of batteries that we prepare, and it's sensitive to high temperatures. So as I already told you, we use some organic electrolytes because we get better electrolyte stability window, though that is advantageous. But what happens at high temperatures, because these salts and the organic solvents degrade. So you get some HF or carbon monoxide inside. It builds up pressure inside the battery, and it explodes. Aging effect and other safety concerns, like you can have dendrite formation in lithium-ion batteries. So what dendrite actually is that you get lithium deposited in the anode part of the battery, and it starts to grow and it reaches the cathode. So when this happens, short circuit occurs. And this is something very undesirable for a battery, and we want to reduce this dendrite formation. So dendrite formation is one of the reasons why we cannot use lithium, pristine lithium, as the anode material. So if you look at other battery systems like sodium and potassium, this is not as remarkable as that for lithium, because they melt, the dendrites that form melt below 100 degrees C. So therefore, it's something very safe to use sodium and potassium based batteries. And today, mostly I'll discuss about sodium ion batteries because this is more relevant to Indian scenario, and we have lots of sodium precursors, practically unlimited resource of sodium with us. On the three sides, we have ocean, and we can really procure sodium. And we can rely on this technology. It's not that we are going to reinvent the wheel. We are going to just build up on the previous knowledge of lithium based batteries and then develop sodium based batteries. So these are the differences between sodium and lithium. It has a larger ionic radius, which means you cannot use the same host of lithium materials for sodium. It's not very favorable. And if you see the distribution, you have practically unlimited distribution of sodium precursors. I mean, you can find this in the ocean, and it's easy to isolate them as well. You do have lithium precursors as well in the ocean, but it's very difficult to isolate them. So however, sodium precursors are very abundant. And the sodium metal has about 1165 milliampere hour per gram specific capacity. So though we have many cathode materials that has been already studied for sodium and batteries, anodes form a major bottleneck for its commercialization because you have to match up with the current day lithium-ion battery system. So now the problem comes where you cannot use graphite because it forms only type 7 intercalation compound with NaC70. So 70 carbon atoms store just one sodium. So that's not very favorable stoichiometry for us. And the specific capacity is very, small, which is 31 milliampere hour per gram. Whereas for LiC6 configuration, what you have is 372 milliampere hour per gram. So we have to depend on some other kind of carbon materials or develop some other kind of carbon materials that can store sodium very well. So here comes hard carbon material. So hard carbon, in the sense, it's more like a disordered carbon material with a lot of turbostatic nanodomains defects. And also you can introduce some heteroatom dopants into this to enhance the storage. So in case of hard carbons, you have a lot of storage sites for sodium to store, like the interplanar spacing in hard carbons is around 3.9 angstroms as opposed to 3.4 angstroms 3.34 angstroms in graphite. Yeah, so you increase the interlayer spacing so that sodium can enter. Also, sodium can store in the voids. Yeah, so there is a lot of possibilities with which you can engineer and tailor hard carbons for storing sodium, and the capacity that such hard carbons can give are even much better than lithium in the recent days. Professor Shinichi Komaba from Japan, he has been working on hard carbon, and his group has synthesized wonderful hard carbon material that can provide us with a capacity of about above 450 milliampere hour per ton. Yeah. So the advantage of using hard carbon is that you can procure it from renewable precursors, which already reduces our cost, and you can scale up the production of hard carbons, and the performance is almost on par with lithium-ion batteries. And here the sodium is the charge carrier, and therefore somehow you can reduce the cost. In case of lithium batteries, you have to use copper as the current collector for anode, whereas in sodium batteries you can use aluminum. That also reduces the cost. So this using of current collector, you can reduce the cost of current collectors, because these days you have the copper's price has been the price of copper has been increasing throughout here. Also, you are getting a very good stoichiometry of NaC 7.4, very near to lithium-ion batteries. Now it's even more with the recent publications. So what are the current knowledge gaps? So the current knowledge gaps in this research area is that the mechanism of how sodium gets stored in hard and soft carbons are not well understood. Soft carbons are those carbons which are disordered initially, but when you heat it up beyond 2000 in inert atmosphere, it gets aligned into graphite, whereas hard carbons doesn't form graphite even if you heat at a very high temperature. Yeah. So there needs to be further improvement in the carbon materials performance. Yeah, if industries have to take up hard carbon as a promising material, it has to show performance way beyond lithium graphite for lithium ion. Doping strategies come into play here, where you can really enhance the storage performance. The importance of solid electrolyte interface in sodium ion batteries is very important. So solid electrolyte interface is nothing but on the when you cycle your battery, on the anode side, what happens is the electrolyte degrades and deposits as an interface between the electrode and electrolyte, and this interface somehow stabilizes the battery. This forms mainly in the first cycle, and it stabilizes the battery. So this interface is ionically conducting and electronically insulating. Yeah. So that is also the property of the electrolyte. Electrolyte should be ionically conducting and electronically insulating. If it's not electronically insulating and if the electrolytes are electronically conducting, then you will be having short circuit within the battery. So you don't want that. And fortunately, the SEI is also something very similar. It stabilizes. And once this SEI is formed in lithium-ion batteries, after that, the battery's performance is very stable. But the composition of SEI, solid electrolyte interface, that forms in sodium-ion batteries needs to be investigated further. How do you tune the solid electrolyte interface? Whether you need a thinner solid electrolyte interface or a thicker one. So this is something you need to look into. So, and interpretations of these, very largely, like the mechanism of how sodium gets stored, their interpretations very largely. Therefore, we need to standardize these things. We need to study how sodium gets stored in much more detail. Yeah. Also, the model for sodium ion storage in carbon materials is not very well sorted out so far. So where intercalation happens, where does absorption happen? Yeah, where, at which point, at which voltage domain? So these things, and what is the effect of oxygen in the carbon material? So these things needs to be studied further. And electrolyte is one of the major component in the batteries, but because lithium-ion batteries were already well studied, people started to work with similar composition of electrolyte for sodium-ion batteries. However, this is not going to be a very good strategy when it comes to sodium-ion batteries, and we need to investigate on electrolytes for sodium-ion batteries, like what kind of electrolyte, whether you use ether-based electrolyte, whether you use ester-based electrolyte in case of organic sodium batteries, or what kind of electrolytes can you use when it comes to aqueous? How do you improve the voltage window of aqueous batteries, whether you use water and salt electrolytes, and so on and so forth. Yeah. So this is one of my work that I studied on hard carbons for sodium batteries, and these were nanoparticles that were synthesized by a simple flame deposition method. So what we did was we treated it with piranha solution initially, and terminated it with carboxyl functional groups, and we found that we really got a very good performance of 277 milliampere hour per gram at 0.1 ampere per gram current density. So this was published way back in 2016, and this was one of my first publications in hard carbons, yeah, and with very stable performance was obtained. If you can see here, for more than 200 cycles, when it was cycled at 100 milliampere per gram, you get a very stable performance, and the specific capacity was also very high at that time, and much better than those published during in 2016. However, if you see the cyclic voltammograms in the first cycle, this was tested in a half cell configuration. Yeah, ethylene carbonate and propylene carbonate were used as solvent, and we used sodium perchlorate as the salt. So in the first cycle, if you see here, propylene carbonate degrades, yeah, in the first cycle of the CV. So this is the degradation of electrolyte and the formation of solid electrolyte interface. However, in the first cycle, you see that the Coulombic efficiency is very low, and this is it's comparable with that of publications related to hard carbons for sodium-ion batteries, where you lose a bit of capacity in the first cycle because of the formation of solid electrolyte interface. However, after the first cycle, if you see the consequent cycles, the curves overlap on one another. Yeah, mostly this looks like a capacitive storage behavior here. And this is the table which compares this work to other works during that time. And we got a very good performance in terms of capacity and also cycling stability. However, the initial Coulombic efficiency of carbon nanoparticles and carboxylated or carboxyl terminated carbon nanoparticles were 49 and 34. Yeah. So we thought that this work was interesting, and we started to use this for preparing binder-free hard carbon nanoparticles. We use the same nanoparticles to study the effect of solid electrolyte interface in these hard carbons, yeah, for sodium-ion batteries. So this is something we thought that this would be interesting to study, because we don't know what effect the solid electrolyte interface or what role it plays for sodium-ion batteries, whether it has to be thick or thin, or yeah. So this was done by Ulrich Rangom, who was a PhD student in Professor Zhao's group. So we both worked together on this publication. So if you see here, we took two different kinds of electrolyte. One was ester-based and one was ether-based. For ether-based electrolyte, we used diethylene glycol dimethyl ether as the salt. So the picture below, this was tested in ether-based electrolyte, and the picture above was tested in ester-based electrolyte. For ester-based electrolyte, we used ethylene carbonate and propylene carbonate mixture as the solvent, and sodium perchlorate as the salt. And what we did was we tested it, and we deposited solid electrolyte interface at very high current density, say 100 ampere per gram, 10 ampere per gram, and 1 ampere per gram. So at these three current densities, we deposited the solid electrolyte interface, and then we started to run the battery at 100 ampere per gram. If you see the figure B, yeah. So you see that when you cycle the battery at so high current density, 100 ampere per gram, so what happens is that you deposit a very thin solid electrolyte interface on the electrode surface. So basically, how the electrode was prepared here was we used an interlaced carbon nanotube mesh, onto which we isolated these hard carbons. Yeah, so we didn't use any binder. We didn't use any current collector. The carbon nanotubes acted as a current collector rather. Yeah. And the hard carbon were just in between these carbon nanotubes now. or the carbon nanotube film. So if you cycle this at 100 ampere per gram, you have a very thin solid electrolyte interface. At 10 ampere per gram, the thickness increases. At 1 ampere per gram, the thickness further increases. So at a very thin, having a very thin solid electrolyte interface affects the performance in such a way that you get a very long cycling stability. That's what you observe here in figure B. Then the orange color one or the blue color one, where the solid electrolyte interfaces are deposited at a lower current density. If you see in figure A, what happens is that you have deposited solid electrolyte interface at 100 ampere per gram, 10 ampere per gram, and at 1 ampere per gram. I mean, deposition of solid electrolyte interface is that in the first cycle, you just discharge it at 100 amps, 10 amps, and 1 amp per gram. Yeah. And then you cycle it for 10 cycles at 1 ampere per gram, 10 ampere per gram, and 100 ampere per gram, and reinstate the current rate to 1 ampere per gram. And you can see the stark difference in the curve where 100 ampere per gram, when you deposit the SEI, it has a very high stability rather than the other two current densities. Yeah, this is for ester-based electrolytes. And for ether-based electrolyte, the SEI deposited is very thin. Whether you deposit at 100 ampere per gram or 1 ampere per gram, it doesn't make any difference. Yeah, therefore, ether-based electrolytes is very much interesting for solid electrolyte interface deposition. And it seems like for sodium-ion batteries, thinner solid electrolyte interfaces are very attractive. So we wanted to see whether there is any difference when you deposit SEI at 1 ampere per gram or 100 ampere per gram. So we did a XPS study, X-ray photoelectron spectroscopy, and these are high resolution scan of carbon 1s, sodium 1s, fluorine 1s, and oxygen 1s peaks. Yeah. So if you see here, it seems like there is not much difference in the composition. Yeah, the composition remains the same whether you cycle at higher current density or lower current density. Therefore, the whole effect comes from thickness rather than change in composition. So if you see here, these are the X-ray-to TEM studies, transmission electron microscope studies. This is the pristine carbon nanoparticle. And here you have the solid electrolyte interface deposited at 100 ampere per gram. So this is very thin SEI. Yeah. And at 1 ampere per gram, the thickness increases. You can see the cartoon below. Yeah, the thickness increases. And this affects the performance, of course. If you use ether-based electrolyte, you don't see much of SEI at all. It's a very thin SEI, whether you cycle it at 100 ampere per gram or 1 ampere. Overall, we see that this is a very nice study where you use a binder-free and collector-free flexible electrode prepared by using these carbon nanotubes into which you have isolated or into which you have placed these hard carbon nanoparticles, and you have tested them with in different electrolytes, ether-based electrolyte or ester-based electrolyte, and you see that the performance is really affected on how thick or how thin your solid electrolyte interface is. Yeah? So this is a study that gives you an insight into type of electrolyte you can use and type of solid electrolyte interface that you need and how to tune your nanoparticles, hard carbon nanoparticles. So we wanted to further improve the sodium ion storage in hard carbons. So what we did was we used the hydrothermal protocol and we enriched these carbon nanoparticles or carbon particles, yeah, with nitrogen, yeah, with nitrogen functionality. So you can see that the interplanar d-spacing is 0.39 here in the figure. Yeah, this is high resolution TEM. And you can see the EDX where you can find carbon, nitrogen, and oxygen on this carbon nanosphere. Yeah. This is the high resolution XPS and this is the survey XPS. So for nitrogen-rich hard carbon, you can see that it has nitrogen functionality from the high resolution, survey scan. And there is not much nitrogen in the pristine sample. Yeah. So the figures beside the one I'm showing with my cursor. So this is C1s high resolution and O1s high resolution. Yeah, this has mostly carboxyl groups and C double bond groups, C double bond groups, CO groups, and not nitrogen functionality. Here, if you see the figure below, carbon 1s, nitrogen 1s, and O1s. So what you see is that you have amide functionality, NC double bond O, and this can also be seen in the carbon, yeah, NC double bond, where C is highlighted here, the star, and here NC double bond O and oxygen. So which means it's present everywhere. Yeah, you can confirm. So it's not a very crude analysis. Rather, this was an involved exercise. It took a lot of time to deconvolute the spectra, and we found that there was some pyrolyc nitrogen, graphitic nitrogen, amide, and amine group. Yeah, these were the kind of nitrogen functionalities in the batteries. I'm sorry. So these are the kind of nitrogen functionalities that we observed in the hard carbon that we prepared. So we tested the nitrogen-rich carbon against sodium in a half-cell configuration. We found that it was 520 milliampere hard per gram specific capacity at 20 milliampere per gram current density. This is a very high, good capacity and high capacity. And here on the right-hand side, if you see the figure below the impedance spectroscopy, C and D, the figure C is the charge-discharge curve, where you can see the nitrogen-rich hard carbons really show a stark increase in capacity rather than the pristine one. However, both of them had a loss in coulombic efficiency in the first cycle, and this is again associated with the formation of solid electrolyte interface on the surface. And if you see the rate tolerance, so we subjected the battery to different current rates, and you see that it's very stable at different current rates. And we started from 20 milliampere per gram, and when we reinstated it to 0.2, 20 milliampere per gram, again, it retained most of the capacity. Both the batteries were, both the electrodes were able to retain its capacity when subjected to rate tolerance tests. However, there is a difference in the specific capacity because of the nitrogen functionality present in the hard carbon. And this is the cycling stability. You see that it's stable for more than 1,000 cycles. And the red one on the top is nitrogen-rich hard carbon, and the one below is one without nitrogen. And we did some ex situ characterizations to understand where this capacity is coming from. Kinetic study revealed some capacity storage. We wanted to see what kind of functional group really was responsible for such performance. Yeah. So which kind of moieties is required, so that you could already design it with such functional moieties to enhance the sodium ion storage. So we did some ex situ TEM and XRD, and apart from that, we did some DFT calculation, collaborating with Professor Deborah Bernhardt from the University of Queensland, where they took graphene sample with the different nitrogen functionalities like graphitic, pyridinic, imine, amine, amide, and pyrolyc groups, and they put the sodium adatom on the top to calculate the binding energy. Yeah, and pyridinic and amine and amide group showed enhanced functionality, and mostly amide group showed enhanced functionality for nitrogen. The binding of sodium is far more stronger than the cohesive energy of sodium in case of amide functional group. What this means is that sodium, instead of interacting with itself and forming the cluster, it likes to interact with amide functional groups. Yeah, therefore that's a very favorable environment for sodium to bind and store. So amide functional group was the strongest. So that is what we found in the XPS curve as well, that we had more amide functional groups. So with this study, we found that the presence of nitrogen is really helpful to boost the sodium ion storage in hard carbons. So this is another interesting work that we did, where we wanted produce hard carbons at a very large scale. So spinifex is a very highly abundant grass, which is, this was carried out in Australia, this research. So this is an endemic grass to Australia, and it covers 1/3 of the land mass. And this is something, considered as a weed. And from this, we produced cellulose nanofibers by a low energy extraction process. And these are the cellulose nanofibers. You see the TEM image below. And these nanofibers, what we did was, this was actually freeze dried and then subjected to carbonization at 1000 degrees C for 4 hours. During freeze drying, what happens is you just remove the ice that has formed inside these carbon nanofibers, and you bring these carbon nanofibers close to each other, and because of the van der Waals force of attraction, these stick together. Actually, we got sheet-like structure. I'll show you in the next slide. And because of this van der Waals force, it comes together. We tested it for both lithium and sodium-ion batteries, and both of them, it gave good performance, and especially for sodium-ion battery. I'll show you the performance of sodium-ion battery in a moment. And if you see the images, the above BC are the TEM images. Yeah, you see how disordered the structure is. This is the carbonized sample, a highly disordered structure. Yeah, the despacing was again 0.39 here as well. And this is the sheet-like structure that we obtained from the spinifex nanocellulose. And this is the EDX mapping that we got. And you can see it's mostly carbon and oxygen here. And this is the grassland from where spinifex grass was isolated. And this is the cellulose, and this is the hard carbon that you get. These are the pictures. Coming to the performance, the specific capacity was very good actually. It was 386 milliampere hour per gram. And even when you cycled it at 100 milliampere per gram, you get 300 milliampere per gram specific capacity, which is quite high. Yeah, and very much comparable to lithium-ion batteries, graphite for lithium-ion batteries. And again, if you look at the figure A, the first cycle again corresponds to the degradation of the electrolyte and the formation of solid electrolyte interfaces. And after that, somehow it stabilizes the system, the formation of ACI, and you get overlapping cycles, which means, there is no further degradation because of the degradation of the electrolyte, even as you cycle it. And you get a very good cycling stability for about 400 cycles. And even when you test it at 1 ampere per gram, at different current densities, we keep on increasing the current rates and reinstate it to 20 milliampere per gram. Again, it shows a very stable performance, and the coulombic efficiency was very good. This work was one example where you could really scale up the production of hard carbons, and these hard carbons can really enhance the performance. Yeah, these hard carbons can really be an inspiration for developing high performance anodes for sodium-ion batteries. So you could further incorporate some dopants and enhance the performance. And this was another work which I carried out, where we wanted to see if this carbon coating can act as a buffer to volume expansion. See, carbon has a very limited capacity. You cannot go beyond that, but you have alloy-based anodes, right? So here we used cobalt sulfide as an anode material, and we prepared a core shell structure using a very simple synthetic route, one-pot synthetic route. And if you see the picture here, okay, I still have some time left. I'm just looking at the time. So if you see the picture here, the TEM images, you see that very nicely coated.
I will request you to finish in another 5 minutes, if possible.
Yeah, sure. Okay, I'll tell as long as it goes, and after 5 minutes, ma'am, you can tell me. I'll stop. Okay, here if you see, this is the TEM image of the carbon shell and the core, which is cobalt sulfide. Yeah, and this is the high resolution, and it's a disordered structure as well on the top, but inside you are able to encapsulate this cobalt sulfide structure, and this is the EDX. So just to quickly show you, this is the sodiation. which means insertion of sodium into these cobalt sulfide. Generally, if you are going to use it pristinely, what happens is that there will be 200% volume expansion. But if you see here, this is the pristine one. When it's discharged, it's in a half cell configuration. So when you discharge, sodium gets inserted into this material, and when you recharge it, you see that there is not much volume expansion. Actually, the volume expansion is just about 17%, yeah, which is opposed to 200% volume expansion. And if you see the cycling stability here, it's quite stable. So 6, 12, 9 are the ratio of the precursor, the cobalt precursor that we are using. So with varied ratios, you can see that you can really tailor such material when you have carbon to buffer, such volume expansion. Yeah. So I'll quickly go through this work. This is an important work because graphite has been used as anode for lithium batteries, and we wanted to try if graphene is something we can look at, because graphene also can be produced in a large scale at a cheaper rate, yeah, economically produce them. So we initially studied, though we got some decent performance, it was not up to the mark, yeah. So we wanted to see if increasing the d-spacing would do the trick. So we increased the d-spacing by inserting these porphyrin molecules inside these graphene layers, and d-spacing increased to about 7.67 angstroms. So these are the HCM images, and this is the TEM image that you can see here, and this is the EDAX. So the very interesting aspect is that we got a very nice performance because of the increased d-spacing. Also, what we did was we rested the battery for a month to see if the battery retains its capacity and continues. So we really saw that, even after 1 month of rest, the battery continued cycling for more than 700 cycles. Yeah, we did similar kind of tests as that of previous batteries, and we saw that through the DFT study how much the spacing of these graphene layers increases, and it increased to about 8 angstroms, and that is what 7.8 we got through experimental means as well. So I'll briefly go through why we have to do research in batteries, at least why is it very important in India's scenario. One thing is that we have lots of car operating worldwide, yeah, but Indian contribution to what is operating there is not much. So most of the manufacturing is either in China or in the US. So Europe is picking up as well, yeah, Volkswagen, BMW, yeah. So, and as I already mentioned to you, that battery is a tank that stores electricity, the fuel, yeah, but this cost is too much, like 1/3 of the cost. If you compare a Tata Nexon petrol-based or diesel-based vehicle to that of electric vehicles, it's 18 lakhs for electric vehicles, whereas it is 10 lakhs for, this Carnot engine-based vehicles, the Tata Nexon. And also, you don't have many charging points. At least where I am in Bhopal, we just have one charging point nearby, just that near the airport. Yeah. So we do not have charging point. That we need to think about how can we, make our footprint in the global manufacturing of electric vehicles. And this needs research. Yeah, this needs technological development. This needs people getting interested, working on batteries. Yeah, India is planning to invest a lot in electric vehicles through startups, through research grants, yeah, and through combined efforts from public organizations and private industries. And the current situation in India, we can already see that the petrol rate is increasing a lot, and most of the petrol is also imported. And see, the Indian scenario is that we will not. It's unlike US or Europe or Australia. Unlike those situations, we have 75% of two-wheelers. Yeah, our mode of transport is two-wheelers rather than four-wheelers. The next after two-wheeler comes the three-wheeler and then four-wheeler. So what we should think about is for two-wheelers. So now for two-wheelers, what would you think? For what? How much whatever it gives per kilometer of the two-wheel? Yeah. So you can think of different strategies, like one thing which is disadvantageous for battery is the charging time. So can we have a station where you can just exchange the batteries? Can you increase the charging time? How can you do this? You need to study the mechanism. Yeah, so we have to devote some research towards understanding the mechanism to build better batteries. We already have the opportunity to leapfrog because many do not own vehicles, though most of them own two-wheelers. Even two-wheelers are not owned by all. So, and now we can incentivize these, and we can already introduce some electric vehicles there. Yeah, and this would be something the government needs to think about, as well as the research. The researchers also needs to think about in bringing out better batteries. Yeah, and what are the challenges that India's battery industry faces is that low mineral reserves.
Wait, can you quickly wind up?
Yeah, sure.
There are some
Yes, ma'am.
questions lined up for you.
Yeah, sure. So we have low mineral reserves. The mineral reserves are very low in India. So we have to depend on alternative technologies like sodium that have shown. But there are other technologies like zinc or potassium ion batteries as well. Yeah. And battery manufacturing is at a nascent stage in India. So we have to robustly work on these and make locally developed technologies available. And we have to, somehow create an understanding of ion storage behaviors in these batteries. And we have to push boundaries of scientific understanding and increase the energy storage so that we have we collectively realize the goal of having zero carbon emission or carbon emission free India. Thank you for this opportunity. I stop here.
Thank you, sir, for this enlightenment full talk. And we have some questions in the chat box. It's from Chinmay Shukla. Sir, when moving in the technological aspect for systems for energy storage, how does a fuel cell compare to the battery system? And even sodium ion, as both are in research stage?
I wouldn't say sodium ion is, yes, of course, sodium ion is in research stage, but both are different systems, yeah, fuel cell and batteries. And when it comes to, I can comment on batteries. When it comes to batteries, especially sodium ion, people have been working now, and there are a couple of companies that have already come up with sodium ion based battery technology. Even recently, I think the Reliance group, this sodium ion based battery technology with Faraday on, yeah, UK company. So people are getting interested in this technology, and there is CATL based company. They have come up with hard carbon based anode and Persian blue based cathode for sodium ion battery for electric vehicles. Yeah, so there is a lot of development, and slowly, I think in the next 2 or 3 years, I'm pretty sure that it will no more be in the research stage. Rather, you will have sodium ion batteries commercially available. Yeah.
Thank you, sir. Sir, another question is from Chinmay as well. That is also when talking about the interface between carbon substrate and SEI, what exactly happens in between them when the battery is in use?
Let me read the question again. Between carbon substrate and SEI. Okay, fine. So what happens is that first you deposit a solid electrolyte interface on the surface of this carbon. So what happens is the electrolyte degrades into different components, say organic or inorganic salts of sodium, and this gets deposited there. Now you do not have any more active surface in the sense for electrolyte to degrade. So what happens? This gives you a channel for ion to pass through. So therefore, the electrolyte does not degrade anymore. Rather, it just ion storage happens, or just sodium passes through these channels that the SEI provides and gets stored there. So this is what happens during battery operation. Yeah, and further during operation, the reason you lose capacity is that sodium forms, non-convertible compounds. I mean, irreversible compounds when it gets stored. Probably it gets stored as clusters within the pores that the carbon material provides. It might not form SEI after the first cycle. Rather, it gets stored in some other compound or some other cluster that's irreversible.
Okay, sir. I hope Chinmay, you got your answer. And one more question is for Bala Murugan Mani. He is asking, Thank you, sir, for your nice talk. Although thousands of materials were studied and reported for batteries, could you explain the major problem in commercialization of those materials? Thank you.
Yes, of course, as you rightly pointed out, there are many materials already made. The problem is that you have to matching the performance of lithium-ion battery is not enough. Yeah, nobody is going to replace the technology that's already existing. It has to have a margin, like it has to be much better in terms of what could you give in terms of energy storage, yeah, or energy density. How much of energy can you give? Can you go beyond? Now it's 350. Can you go up to 650 using sodium-ion batteries? Is that possible? So such kind of material tailoring is required, and you have to reduce the battery weight. That is only possible when you have better energy density, right, for your batteries. So even though we have many materials, it needs to be engineered to match, not just match the current standards, rather exceed the current um, energy density that we get. That is what I think.
Okay, sir. Thank you. So, ma'am.
Yes, any question from the panelist side? Okay, Rohit, I will ask a couple of questions, although I get enough time to ask you, but quickly. So what is your opinion like? Is it that the scientific community is no more taking interest in this lithium-ion battery technology and just pushing towards the sodium-ion battery? That is something I would like to ask one. And then while you were discussing this ether and ester-based electrolyte, the test that you have done, what was the hypothesis of using these two things-based electrolytes?
Okay, so I'll answer the first question. So it's not that people are not wanting to do research in lithium-ion batteries. As I told you that there is a problem with this dendrite formation that forms at the anode, and you can have the short circuit because of this. People have gone to solid-state electrolytes. So this is what is being researched these days in terms of lithium-ion batteries. So solid-state electrolyte is the next upcoming technology, and it's sodium-ion technology is not going to replace lithium batteries as a whole. Probably sodium batteries comes into play where in grid level storage or something like that, but lithium battery is going to be there for the next coming decade. And the research area is solid-state electrolyte, because you can avoid many problems with respect to thermal management and other things. And when you use solid electrolyte, you can already use lithium metal as the anode. Lithium metal gives around 10 times the capacity of graphite. We are not able to use it in organic electrolyte based batteries is because here you can try to avoid the lithium dendrite formation, though it's not completely avoidable, because even a small disorder within the solid electrolyte can, because of the size of lithium ions, it can just pass through it. So there is a lot of work going in this area, and this is the next upcoming technology, and this is what the scientific community is researching about, I think so, in lithium batteries. Yeah. And for the second question, ether and ester-based electrolyte, our hypothesis was we wanted to find out the effect of SEL. So we wanted to choose two electrolyte solvents that has very varied SEI composition. Therefore, we came up with one ester-based electrolyte and other ether-based electrolyte to see if there is any difference in composition of thickness. So this is how we studied that battery. Yeah. I hope I answered your question.
Yes. I think anyways we can discuss later also. So I would like to thank you for your excellent talk and excellent publications.
Thank you.
Best for your future. And so we can let's all thank Dr. Rohit Gaddam for his excellent talk, and we can move forward for the next talk. Thank you, Rohit.
Thank you, ma'am.
Over to you.
Thank you, ma'am. Thank you, ma'am. Our next talk of this segment will be by Dr. Monica Khanuja. Dr. Khanuja is currently associated with Center of Nanoscience and Nanotechnology, Jamia Millia Islamia University. She has experience in fabrication of various nanomaterials having applications in sensing, antimicrobial, water disinfection technologies, etc. Using different physical and chemical routes. She has research interests in synthesis, investigation, tailoring two-dimensional materials and their heterostructures to pave the way for the new era of photocatalytic water disinfection and water splitting. Today, her talk will be on advanced nanostructure materials for environmental sustainability. On this note, I welcome Dr. Khanuja to this platform. Ma'am, you have 25 minutes to conclude your session, and after that, 5 minutes of question answer. Over to you, ma'am.
Okay, thank you very much, Dr. Pooja, and I'm thankful to the Committee Institute of Nanotechnology Director, Dr. O.P. Sinha, and this course workshop organized by Dr. Ranu Nayak, Dr. Nidhi Chauhan, and rest of the respectable nanotech faculties. So, my slides are visible to all of you?
Yes, ma'am.
Yes, Dr. Khanuja, you can put it onto slideshow mode.
Okay. Is it fine now?
Yes.
So thank you. So title is this Advanced Nanostructure Materials for Environmental Sustainability. So this is our center at Jamia Millia Islamia. Our research collaborators in this image, and most importantly, Professor Izima, inventor of carbon nanotube. All right, so this environmental sustainability, basically here we are talking about from this image, it's being clear that rivers are dying due to the dyeing process, because textile industries are mainly responsible for water pollution. So this environmental pollution is one of the most important global challenge nowadays. So under this environmental pollution, environmental sustainability, I will focus on this water pollution part. So you can see that most of the rivers now look like a rainbow because of the textile industries, which are mainly responsible. And there are different type of pollutants are responsible for different type of textile dyes. These methylene blue, orange, rhodamine B, Congo red, just to have a colorful clothes. Then we have heavy metal ions. So whole this Ganga Brahmaputra belt, people are suffering from not many diseases because of the heavy metal ions present in the water. Then we have some toxic chemicals, and nowadays one most important problem is with the antibiotics that also being result in the development of antimicrobial resistance. So we'll focus on these degradation of these materials to purify the water. So we clean it and then we'll recycle it. So these are the materials that we use for the degradation process based upon the photocatalysis. So as mentioned that during this COVID-19, use of antibiotics has increased enormously. Now every antibiotic or every medicine come with expiry date. So after this, after 1.5 years or 6 months, we used to simply dump them. But finally, this will result in the AMR, which is again the global issue. So when we talk about the global issues, these are like energy crisis, environmental pollution. Now this is one most tremendous is this AMR, which is very much pronounced after COVID-19. So not only human life is affecting the aquatic life also. So you can see that a lot of fishes, they are not able to survive in this toxic water. So overall focus of the research is degradation of textile dyes, these heavy metal ions and the antibiotics present in the water. So for the degradation of all these, basically we are working for goal number 6, Sustainable Development Goal by this. So it's clean water and sanitation for all. United Nations given some sustainable goals, clean water and sanitation, clean energy for all. So our focus is on goal number 6 of United Nations. And second is this alignment with our own government is taking a lot of initiatives like Swachh Bharat Abhiyan. And like in Goa and all this, it's called Har Ghar Jal Rajya. So water to be available to the every household. Then lot of budget is also being allocated under this.
Louder.
Water is this also being allocated lot of budget that is under this Jal Jeevan Mission. Okay, so we have our research is in alignment with the current requirements, and we are using this process of photocatalysis, which is involving the 3 steps, basically utilizing the sunlight and then generation of electron hole pairs. And finally, these electrons and holes are used for the generation of RO species, which are going to degrade the pollutants present in the water. Some limitations are there. That's why we are looking for the advancement in the nanostructure materials related with their band gap, related with the electron hole recombination. So till now, in many of these water pollution degradation problems, we prefer to use zinc oxide materials. So zinc oxide based materials, these are very common and very popular. Means if you look at the research publications, out of 150 or 60 earlier used to be based upon zinc oxide only because of its tremendous applications, whether it's in antimicrobial resistance or packaging industry or in electronics, many more, because of its morphologies present, different morphologies. So here these zinc oxide rods are prepared by thermal decomposition method at different temperatures, different aspect ratios are obtained. And these different aspect ratios result in the different surface area. So when we talk about the nanostructure materials, the important points are these surface to volume enhancement. So surface area enhancement is determined using this BET analysis technique. Now, second, we talked about the quantum effects related with the band gap tuning. So here, in order to enhance the degradation property of zinc oxide, it's being doped with the copper. So once it is being doped with the copper, degradation efficiencies, as clear from these histograms, which are yellow in color for copper doped ZNO rods, it's much more higher as compared to the pure samples. Not only the efficiency, but the rate kinetics has also increased almost 3 to 4 times when we have doped samples. So with these advancement in structures, means by doing this doping and forming the composites, we have a reduction in the recombination rate, as well as we have more utilization of sunlight, because band gap is now not only in the ultraviolet range, we have enhanced utilization of sunlight when we have doped copper structures, because pure zinc oxide having band gap in the ultraviolet, and ultraviolet is only 4% of the sunlight. So if we use ZNO based structures, then we are using only 4% of the sunlight for the degradation process. So by having the dope samples, you can see that these samples in this image are able to degrade the methylene blue and some mixed samples also, which we have collected from river also, or from say textile mill also, this methyl or isocyanide dyes as well as anionic dyes, it's able to degrade. Now again comes the important point that here not only this degradation part of textile dyes, we also have this killing of the bacteria also that are present in water, because these are mainly responsible for the diarrhea, jaundice, waterborne diseases that are there. So you can see here the cell lysis, and that whole cytoplasmic content will come out once nanomaterials interact with these bacteria present in the water. So not only doing the purification of water in terms of degradation of organic pollutants, but also by in terms of killing these bacteria present in the water. Now further advancement is nowadays done in terms of the 2D materials. So there are a lot of 2D materials which are very popular, like graphene, this 2D based transition metal disulfide, graphitic carbon nitride. So in our lab at our center, we are working on these material synthesis and their application. So one of these is TMD is MOS2. So it's basically beyond graphene we are talking about. So you can see that these 2D materials in the nanoplates, you can see at different scales. Advantage is that their band gap is in the visible range. Tunable properties means when the change of the number of layers can tune the band gap also. Now some limitations also again will do some kind of advancements to do the improvement in the photocatalytic efficiency part. So here this pure synthesis is done by hydrothermal method, and their composites also by doing this in situ oxidative polymerization method. So for more details, some references are mentioned which were the work is being published in these papers. So here by having the polymerization with the conducting polymer, it overcomes the challenge of poor conductivity. So here you can see that when we have this pure MOS2 and when we have this its polymer, the interlayer spacing has been increased from 0.67 to 0.75 nanometers. So basically this increase in the interlayer spacing results in the van der Waals interaction among the layers. So once this van der Waals interaction is reduced, so we can overcome the problem of agglomeration. So for the practical applications of all nanomaterials, there are some criteria like that. All of them have uniform size, morphology, and particles not to be agglomerated. So by having these polymer composites, disadvantages of pure MOS2 can be overcome. So this is one more schematic to clarify the mentioned point that how this interlayer distance is enhanced when we have the composite with the conducting polymer. Now, the technique mentioned previously is this hydrothermal, which is bottom up for the students who are interested. So liquid phase exfoliation is also one of the most popular technique to prepare these 2D nanosheets. So liquid phase exfoliation and then this mechanical ball milling are very common and easily can be done in the laboratories or research labs for preparing these 2D nanostructures. So depending upon the solvent, one can choose the best combination for preparation of or for tuning the number of layers. Now here further we have this MOS2 carbon nanotube. This also plays the same role. Again, the enhancement in the interlayer spacing, and finally the problem of agglomeration is overcome. So these now MOS2 and WS2 heterostructure is prepared to have more control over the recombination process. So these are the high resolution transmission electron microscope images to show that MOS2 WS2 heterostructures. So one can clearly see that here we have WS2 nanorods and MOS2 nanosheets. So this 2D 1D structure also results in the enhancement in the recombination. This recombination process is very important because this is the key step which decides the final degradation efficiency of any photocatalytic material. So from these time interlayer spacings, it's easy to locate the regions of these sheets and rod-like structures, and number of layers are also countable using this. Now, further has been mentioned that second material that we prefer is MOS2. Now here the sulfur is replaced by selenium. Advantages are further that here we have more control over the number of or the morphology. And this material is quite fast in its degradation efficiency because of its large surface area. And so here by changing the or by doing the optimization the precursor conditions, we have room shaped, then we have sheets and nano urchin or flower like morphology also. So different pH conditions or optimization of initial parameters help in this. Again, also we have prepared composite with the polymer to further do the enhancement. Not only making a composite is important, but also doing its composition optimization. So here the different proportions are being done. 1:1, 1:2, 1:3, 2:1. Now the reason behind it will be clear because this MOSC2 and polyethylene both have a different surface charge. And surface charge is important because here you need to do the interaction of the photocatalyst with the adsorbent. So electrostatic interactions are important, and for the electrostatic interactions, we are interested in the determination of surface charge using, we have done it using zeta potential measurements. So here not only the cationic dye, by doing the optimization in the composition, surface charge is optimized. So the given material is good for both cationic as well as the anionic dyes. So rhodamine B, which is a very complex dye, and Congo red are degradable through these materials because of the optimization of charge. Now similar composite is done with MOSC2 PPY. Now why again one more polymer is being taken. Now here the advantage is that this is the 24/7 photocatalyst, which works during the day as well as night also. Mechanism is also explained. So here the first is the optimization of surface charge, and then comes the ability to degrade both in dark as well as in the light also. Now, when we talk about the recombination rate, here we use this time resolved photoluminescence spectroscopy. So when we have different composites, then this MP21, which is best in terms of the surface charge, is also best in terms of the recombination rate. So here, if you see the tau, then it comes out to be the maximum for MP21, which is 16.71 as compared to its pure or rest of the composites. So degradation efficiency reason of being why this is most efficient is explained on the basis of these PRPL studies. So round the clock photocatalyst, as mentioned about this MOSC2 PPY. So degradation is in the light also as well as in night also. Reason is that it has some charge particles. So in the night also it's able to form the radicals, ROS species, which finally interact with the pollutants for its degradation. Now, it's not that we used to get the complete degradation. Basically, we left with some intermediates, then we look for these intermediates, whether they are, how much they are toxic. So two studies usually carried out for this. One is this HPLC, which is high performance liquid chromatography, and LCMS. So LCMS is available at our Jamia CIF center, and HPLC we did it at IIT Delhi. So to know the products that what is we are left with. So the rest of the products are not as much toxic, or we are able to know what is the degradation pathways followed. So not only doing the degradation, understanding the mechanism, and then the degradation pathways of these to know the whole in and out of the process. Now, initial slides, I mentioned that we are targeting heavy metals. Now we are targeting textile dyes, and we are targeting antibiotics also. So here the material is used for the degradation of tetracycline, one of the very common antibiotic. So here this M/Z ratio which decides the product. So here the products we get at 464-33, but they are not as toxic or as means giving rise to the AMR as compared to pure TC. So these studies are also important when carrying out the degradation process. Now comes scavenger and reusability. So we are not only have to clean it, we have to recycle it also. So it's being tested for a number of cycles. Now scavenger studies also being done just to know that which RO species, because like hydroxyl ion holes or this superoxide radical, which is playing the dominant role. So two ways to do this. One is carrying out the scavenger test, and second is by doing this EPR studies. That is electron plasma resonance. It's not right now slide report, but it's also a good technique to know about the mechanism. We'll discuss that EPR later also. So recyclability is done. So sample is good, can be easily used for the number of cycles. So after this advancements, so okay, different conducting polymers, doping. Now here comes the metal organic frameworks, which are pores. So these materials are very good in terms of number of active sites and the surface area. So this composite is basically successful in the degradation of mentioned antibiotics, that tetracycline and rest of the antibiotics which being very popular. So combining this, so using these MOS2 nanostructures, we are able to degrade the dyes also, and this heavy metal chromium also, and antibiotics also. Now Further, no problem as mentioned that MOS2 with selenium is toxic, itself toxic. So to have further biocompatible nanomaterials, we have prepared this WS2 also. Here, this optimization is done to obtain different morphologies, sheets and dots. And these are also being studied in terms of their ability for degradation of pollutants. As mentioned, for more details, you can refer these published papers. So here, we have malachite green, which is again a complex molecule. So here in this 0 to 180 minutes, you can see the change in the color. So this photo is specially chosen because it's being selected for the cover page of journal. So 0 to 180 minutes, you can see that even after 15 to 20 minutes, the given WS2 composite is able to degrade this complex dyes. Now here you can see, although the material water become colorless, but it's not that it's completely degraded. That's why the study of intermediates is of high importance. LCMS studies, HPLC studies need to be done. Further, this sample is being used for this pulmonary toxic drug, which is nitrofuran. So here again, it's being done as a function of different photocatalyst composition to know the mechanism, whether pseudo first order or second order kinetics is followed. So on that basis, it's also easy that what kind of interaction is taking place. So changes to be done either in terms of the surface charge or in terms of the surface area, which is going to play the more crucial role. So it's important to understand the mechanism. So here you can see these three plots which are done to know the pseudo first order model, second order, which is, so here this pseudo first order model is followed as evident through this R square values. So this is say that 0.96. So first order means that van der Waals interaction is happening between the photocatalyst and the adsorbent. So K is the rate constant, and for different concentrations experimental to know rate kinetics process. Now this 4-chlorophenol again, usually people don't believe the ability of photocatalyst only by its ability to degrade the dyes, because even if you put the methylene blue under sunlight, it will show the decoloration. So it doesn't mean that no intermediates are present. So these colorless pollutants are also important. So to doubly sure about the photocatalyst, its efficiency, its kinetics, take some colorless or more complex dyes. So again, HPLC study is being done. So compared also in terms of nanosheets and nanorods. So for nanosheets, only one, and multiple peaks are present in case of nanorods, just to show that lot of intermediates are there. So material is not at all degraded completely. So this is a list of the intermediates. So both HPLC and LCMS work on different principles. In LCMS, M by Z ratio is important. And here we look for the different tension time values. So these are the different intermediates that we obtain when we use, when this 4-chlorophenol is used as a model catalyst. Now one more, this material which is taking a lot of attention nowadays is graphitic carbon nitride. So graphitic carbon nitride is again a two-layered material. Now here the advantage with respect to the rest of this, that this is easily prepared through thermal decomposition process. Now both this MOS2, MOSC2 prepared by hydrothermal, now yield is very less. Now here, as you see, that we need to do the purification of the whole river. So much of water is polluted. So we need the material also in the bulk quantity, easy production and scalable. So graphitic carbon nitride possess all these advantages, and this material is very much popular in supercapacitor or batteries application. So again, this further to enhance its ability, its composite is being formed with the polymer. So it helps in the reduction of agglomeration problem. And again, further advantage is that when we have this polymer, then it results in the enhancement in the surface area also. So we have different composites, and the surface area increases with the increase in the polyaniline composition. So BET technique works on the principal absorption and desorption of nitrogen. So with this, I want to conclude, and so many materials being discussed, so many research facilities being involved and preparation. So with the help of given fundings, it's being possible. And thank you very much. So these are our collaborators from Jamia and rest of the Delhi. My PhD scholars, I'm thankful because they are working in this, making different materials for different applications. So these are the scholars. So thank you. So basically, we have to conserve the resources to preserve the future. Thank you.
Thank you, Dr. Manika. Pooja, would you like to ask the questions?
Yes, ma'am. There is some question in the chat box. P. Bhatnagar is asking that what is the band gap after doping by copper?
Yeah, it has been, say, for pure, it has been changed by 0.1 to 0.2 electron volt when we dope with the copper. Main advantage is that we have enhancement in the sunlight absorption. So more sunlight is available for the photocatalytic degradation process. And second, the key point here is that rate of recombination is reduced when we have pure ZNO doped with the copper. So now electrons and holes are available for the formation of ROS species.
Okay, ma'am.
I think this is Bhatnagar sir asking question, if I'm not wrong.
So, ma'am, another question is from Garima. That is, as you are working on dye degradation using different type of nanomaterials, my question is how band gap affect degradation of dye and why different effect of same nanomaterial on cationic and anionic dye is observed?
So as mentioned, band gap is important because in solar spectrum, only 4% is UV light. So earlier problem with the using ZNO or titanium oxide, although being so much popular, but they use only 4% of the sunlight. So in order to make the process, photocatalytic degradation process more efficient, we have to have a visible light driven photocatalyst materials. So all these mentioned 2D materials have band gap in the visible range, and visible range is 47% of the total solar spectrum. Second point is that how I am able to do this degradation of both cationic and anionic. So it depends upon the surface charge. Electrostatic charge is the key role. Here, this example is given of this MOSE2 polyaniline composite. So it's being prepared in 1:1, 1:2, 1:3, 2:1. So MOSE2 is negatively charged, whereas polyaniline is positively charged. So their different compositions result in the presence of different surface charge. So when we have the composite of 2:1, then both the charge centers are there on the surface of the photocatalyst. So given material is able to degrade cationic as well as the anionic dyes. So some more details and this mechanism part is discussed in two papers. One is dyes and pigments. This is a general name published in 2020, and one is more separation and purification technologies, 2022 publication. So in both these details, mechanism and how the given photocatalyst is capable enough for the degradation of both cationic as well as anionic as well as heavy metals also.
Okay, ma'am. Thank you, ma'am. Another question is from Rohit Sharma. That is, thank you, ma'am. How you prepare the MOSE2 and Pani composite?
Okay, so to prepare MOSE2, we use hydrothermal method, which is a bottom-up approach. In our lab, we have prepared MOSE2 using liquid phase exfoliation method also, which is top-down, so both can be used. But to have the control over the morphologies, like mentioned in one slide, that it can be broom-shaped. Broom-shaped means high aspect ratio. One-dimensional nanostructures are very good for the reduction of recombination rate. And nano archins, nano sheets. So all these control over the morphology is possible using this hydrothermal method. And by using this top-down approach, liquid phase exfoliation, number of layers can be controlled by varying the solvent and varying the time. But problem here is that pure MOSE2 is very expensive. So 10 gram means 10,000. Similarly, WSC2 is very expensive. 10 gram means 50,000. So we need to look for these factors also.
Okay. Ma'am, there is another question from Chinmay Shukla. That is, ma'am, how do you analyze which all materials to use as photocatalyst in degradation study? Also, do you use your materials without any protective layers, just active materials?
Yes, at presently we are using them as it is and then trying to take them also for the recyclability. But yes, we need to use some layers, especially when we have MOSC2 because selenium is toxic in nature. And decision is being done that which material to be used. Like I'm very much satisfied with the WS2 and its composites because of its biocompatibility. Okay, but in many cases we are not looking for the drinkable water. We want simple cleaning of the water. And when we only want the simple cleaning, then we'll go for this MOS. It's very fast.
Okay, ma'am. Thank you, ma'am.
Yes, Dr. Monica, thank you so very much for first accepting our invitation, being on time, finishing the talk. So we have been interacting in the past quite often, but still I'll ask you one question here. I see that you've been working on MOS2 and WS2 and even graphitic carbon nitride composites. So first question, I think PANI is probably the most favorite conducting polymer. Is there anything else scientists are working on? And secondly, do you see any chance that these materials, like now that people are able to make them in large scale, are in the pipeline to be used commercially for dye degradation and all?
So preference is basically for the large scale production. Okay.
Right.
So for this graphitic carbon nitride is the first choice. Second reason is economical. And as far as conducting polymers or other polymers making their composites are concerned, preference of PPY over polyaniline is there because it's the 24/7 photocatalyst, even in the dark. So I can't say it's a photocatalyst, it's a catalyst which can work 24/7. So just to increase your efficiency, one can say that have your collaborations all over the world. When you are sleeping, let other person use work. So same is this MOSC to PPY. Even during the night, when no photocatalyst is working, this is able to do the degradation. Now, other than this polyaniline and poly PPY, people prefer this polythiophene also, but here this is again, these precursors are quite expensive of P3S and all this. So point is again, you need to look for the economical materials and large scale production.
Right.
Then only one can implement for these global challenge solutions. Issue is global, so production has to be at large scale only.
True. Okay, Dr. Monica, there's one more question in the chat box. I see that it says, is it possible to degrade all the dyes, I mean industrial waste dyes, practically?
Yes, we have done on multiple dyes, even many complex dyes also. So our next plan is basically to take some samples from the textile industry of some Surat. We have in collaboration with them also that and see. Actually, there are many challenges that that given sample has how much its concentration is there and charge. So when the sample or this polluted water has multiple dyes, okay, that charge part we can handle by having the optimization on the surface charge. But its composition also important. So that's why in some studies we have done it as a function of photocatalyst concentration. So how much concentration of the catalyst is required for the degradation. So all type of programming to be done to get the best materials for the even more.
It is a really good talk, and I know you are working with that much dedication. One thing which is really contradictory to each other, when we are talking about the photocatalytic property, we generally try to take the wider band gap so that we can have the more absorption and the efficiency can increase. While when we are going for the MOS2 or the other TMDC materials, basically they have the lower band gap. But if we go for the experimental output or experimental finding, these TMGC materials are showing the better response compared to the wide band gap materials. So is any specific reason for that?
Yes, you are totally right. Yes, it's a contradiction. Yes, because photocatalysis process is principle basically involves two steps, that is utilization of sunlight. So utilization of sunlight means if we take wide band gap semiconductors, then utilization of sunlight is less because ultraviolet is only 4%. But more importantly, not this band gap is important. Important is the reduction in the recombination rate, which is the step that decides the efficiency of the photocatalyst. Although zinc oxide possesses band gap in the UV range, but still it's quite very much efficient as compared to MOS2, which is visible light driven. Or when we have this copper doped zinc oxide, it's much more effective because when we have to control the recombination process. That's why this TR film studies is much more important than finding the band gap tuning or band gap change after forming the composite. So once you have the control or once you have the enhancement in the recombination process, the given photocatalyst will work fine.
So it means that we can play with the indirect band gap material instead of the direct band gap material. Because
Yes,
if you are
yes.
controlling the direct band gap, you are controlling the electron hole pair recombination.
More important is to control the recombination process, not the band gap.
Yes. Okay, thank you.
Thanks a lot, Dr. Manika Kanuja. Let us all thank the speaker and let's move on further. For the next speaker, over to you, Pooja.
Thank you, ma'am. Now we come to the third talk of the day. That is, the talk is by Dr. Kalavati Shaini. Dr. Kalavati Shaini, currently an associate professor at Miranda College, Delhi University. She is PhD in chemistry from University of Rajasthan. Her research and teaching career includes several awards and fellowships. She has given research guidance to several UG/PG students. She has several research publications and also has participated in many conferences. Her research interests include electrochemical and hydrothermal synthesis of new metal organic framework and their applications, electrochemical synthesis of nanomaterials, design and synthesis of advanced functional materials for renewable energy, electrocatalysis, photocatalysis, CO2 electrochemical reduction to hydrocarbon, fuel cell, electroanalysis, design and synthesis of electrochemical sensors. Today, her talk will be on the use of green synthesized nanomaterial for anti-cancer, anti-diabetic, and antibacterial application. Ma'am, you have 25 minutes to conclude your talk, followed by 5 minutes of question answer. On this note, I welcome you, ma'am, to this platform. Please take the stage. Thank you, ma'am.
Thank you, Pooja. My slide is visible to you?
Yes, ma'am.
Yes, your slides are visible, Dr. Sanik. If you can please put it onto slideshow mode and your voice will be
One
a bit
request
louder.
of me, ये जो आपका विंडो आ रहा है ना, the meeting is being in live stream जो भी है इसको एक साइड में कर दीजिए because it is focusing on the slide. It is not easy to.
I didn't understand, ma'am. What are you trying to say?
आपका जो ये मीटिंग रिकॉर्ड हो रहा है लाइक दैट मैसेज जो आपका बिल्कुल हम जो भी प्रेजेंट कर रहे हैं जो भी स्पीकर है उसके ऊपर आ रहा है ना स्लाइड शो पे, तो आई थिंक ऑडियंस के लिए इजी नहीं होगा व्हाटएवर स्लाइड शो इज.
What we are able to see is fine. I think you can carry on. Because there is a, I mean, I think you're trying to say the way we are able to look into the speakers. There is a way we can actually change that also on our own. So for us, we can see your slides. Will you share again, ma'am? Dr. Sunny?
It is disconnected.
Semiconducting material is a material having conductivity between metals and insulators. Semiconductor materials are usually extrinsic and intrinsic. So, intrinsic semiconductor is usually the purest form of element.
Dr. Saini, am I audible to you? Ma'am, am I audible to you? Pooja, will you check if she is there in the meeting?
Yes, ma'am.
I don't think she's there in the meeting. Let's wait for one more moment.
No, ma'am, I think she is not joined.
You can call her.
Doctor,
you can call her and check if there is any net issues.
Yeah, Dr. Nidhi Chauhan, may I request you to call Dr. Sani? Dr. Nidhi? Okay, kind apology for this short wait. So Dr. Kalavati Sani is trying to rejoin again. So let's wait till she joins. Okay, I think because she's taking some time, maybe what we can do, we can start with the next lined up talk. And as Dr. Sani joins, then she can deliver the talk because the next talk is going to be short. So meanwhile, we can have another talk. Okay, Pooja, please go ahead.
Okay, ma'am. So our next talk will be by Young Achievers. The first talk will be by Mr. Abhayavartin Selvam. Mr. Abhayavartin Selvam is currently pursuing his final year of BTech MTech in nanotechnology from Amity Institute of Nanotechnology. His research interest includes metal organic frameworks, carbon materials, photothermal applications, biosensors, etc. He has published in reputed journals on the same. He is the winner of Hindustan Petroleum Corporation Limited's New Generation Ideation Contest 2021 for his topic Metal Organic Framework Based Janus Solar Absorber for Effective Photothermal Desalination. Today, he is going to give a talk on insight into photothermal water desalination. You have 12 minutes to complete your talk, and there will be 3 minutes of question and answer session. Over to you, Abhayavartin.
Thank you so much, Ms. Pooja. So is my screen visible?
Yes, sir.
So good evening to one and all present here. I'm Abhyarthan Selvam and I'll be discussing on the insight into photothermal water desalination. And this will be on the context of our recently published review article in Solar RRL. So before I begin, I would like to give the background to the problem, which that is everyone knows the distribution of water, which is mostly seawater and a small percentage of fresh water. And we have exhausted this fresh water dramatically over the past decades. And now we rely on utilizing the oceans to satisfy our day-to-day needs. And these oceans and seawater, as we know, are hypersaline water, for which various technologies, desalination technologies, have been introduced to overcome that. However, they also come with certain drawbacks. And these drawbacks are that they require large amount of feed water, energy, and chemicals to actually produce the fresh water, thereby releasing brine and greenhouse gases, which gives a very difficult environmental implications. So photothermal desalination was then suggested. And the need for photothermal desalination in India is a very important factor because Niti Aayog has recently reported in their composite water management index that 40% of India's population would not have access to safe drinking water by the year 2030. Hence, they've also set up desalination plants along the coastline because they have understood that India is abundant with their solar intensity and specifically in the coastal areas, having the maximum solar intensity. And moreover, 33% of Indian border is covered by the coastal area. Therefore, this technology would be highly crucial to keep in our arsenal. Moreover, going on to the photothermal materials. So conventionally, they have been classified into metallic nanostructures, inorganic semiconductors, carbon-based materials, and polymeric materials. And depending on the classification of material, there are different modes of photothermal conduction. So they can be plasmonic localized heating, non-radiative relaxation, and thermal vibration in molecules. So there are certain parameters before designing a photothermal material that needs to be considered. So this particular figure shows the evolution of different photothermal materials since the year 2016 when this field has emerged in a large scale. So certain parameters such as broadband absorbance, which basically means these materials should absorb light from the UV region up to the near infrared region with robust photothermal conversion efficiencies, and thereby they should avoid thermal energy losses. And these 2 points are actually interrelated if you consider the fact that certain materials which have like these flat surface based materials or nanostructures, what they tend to do is even though they can absorb good amount of light, they are lost due to transmission or reflection, and thereby not enough is there to actually convert the photos into thermal energy. Hence, scientists have designed porous structures, and they've seen that porous structures have shown better photothermal efficiency. And this is due to the absorption of light in their pores, which allow more light absorption and thereby more photothermal conversion. Furthermore, longevity and recyclability are also 2 important factors for its practicality. Another important factor is the heat balance in a photothermal interfacial evaporation system. So as we all know, the absorption, reflection, and transmission are important factors when it comes to the photonic part. But in the thermal part, the heat tends to get dissipated through convective, radiative, and conductive modes. And specifically, conductive heat losses is a major problem when it comes to a photothermal system because they tend to heat up the bulk water, and we focus on interfacial evaporation. And the reasons will be discussed in the further slides. So understanding that heat conduction losses can be minimized by 2 strategies. One is an extrinsic strategy and the other is an intrinsic technique. So creating insulating structures are extrinsic strategy, and using materials that have lower thermal conductivity are intrinsic techniques. So moreover, in the extrinsic strategy, microporous materials can be used and bifunctional structures. So these bifunctional structures, what they do, particularly in the applications of steam generation and desalination, is that they are able to pump water continuously as well as act as thermal barriers, thereby insulating and can allow localized heating of the interfacial. So capillary action plays a major role in this particular function, as it is the backbone of the photothermal desalination technology. So one such example is the mangrove tree. So as we all know, mangrove trees are able to sustain in highly saline condition, which is due to the capillary action that takes place in their roots and which helps with the salt rejection as well as the transpiration of this water or pumping of this water to all the parts of the tree. So similarly, we can design nanostructures which can mimic this capillary action, which would help with the salt rejection and prevent salt accumulation. Moreover, pump the desalinated water up to the interface so that it can facilitate the solar-driven steam generation. So there are, as I previously mentioned, there are different modes of this solar-driven steam generation, and particularly we choose interfacial evaporation. So there is bottom heating, bulk heating, and interfacial evaporation, with bottom heating and bulk heating being a more energy consumptive process, and it is not very effective. Therefore, interfacial evaporation is chosen better because it doesn't require as much as energy compared to the other two techniques. And moreover, because they only heat at the surface of the water, the process of vaporization becomes quicker. And this interfacial system can also be further classified as into direct contact using single layers, indirect contact, or through isolation by creating different structural pathway like 1D path or 2-dimensional path. And finally, they can also be completely isolated from the water. So currently, research is being done using these theoretical knowledge by developing different nanostructures which are in their experimental phase. So first is the nanomembrane. So when scientists started using nanomembranes for this particular application, they chose the hydrophilic membranes initially because they thought that the water pumping would be better using hydrophilic membrane. However, the problem they faced was the membrane fouling. Hence, they moved on to utilizing hydrophobic membrane. And although it was preventing the membrane fouling by rejecting the salts, but it did not actually have that good of a steam generation efficiency or allowing better photothermal conversion efficiency. So what scientists then further did was utilizing Janus structures. So Janus structure incorporates a hydrophilic as well as a hydrophobic membrane, wherein the hydrophilic membrane would help with the continuous water pumping, and the hydrophobic would help with the prevention of salt accumulation and salt rejection. Thereby, the solar absorber can vaporize the water that happens at the interface of this hydrophilic and the hydrophobic membrane. However, they also face another drawback, which was their solar absorber. As I previously mentioned, that the flat surface, in this particular case, they've used a carbon black, which has a flat surface kind of a nanostructure. So to overcome that, they went into porous materials, and one classification of that is the reticular materials, such as metal organic frameworks or covalent organic frameworks, which are basically porous materials and allow better absorption of light and thereby better photothermal conversion efficiency, which have also shown better desalination percentages. So particularly in desalination, it's not only about steam generation, it's also about collecting this water. So this schematic illustrates a basic idea of how a photothermal setup would be, where in the evaporation chamber, the seawater would be taken and then evaporated. But then this glass pane over is actually inclined at a rough angle of 50 degrees. And what happens is that this glass pane is coated with a hydrophilic side and a hydrophobic side. So these vapors are collected at the hydrophilic coating, and then they are taken to the collection chamber because of the inclination. And the hydrophobic coating helps with the droplet formation and thereby can be collected in the collection chamber. So currently our lab is also working on metal organic frameworks as an effective solar absorber for photothermal conversion and photothermal desalination. So we particularly use a copper-based MOF, which is the HKUST1, and also added nickel doping to it and calcined both the samples. And what we observed is the formation of different copper oxidation state in the case of CO2O, CuO, and Cu. Moreover, while doing the FTIR for the uncalcined sample, it was observed that the CuO peak, which is observed at 730 centimeter inverse, is elongated. The intensity is more in the case of nickel doping. So similarly, we also did the Raman for the samples of calcined and uncalcined. And what we saw was the ID by Ig ratio was 1, which suggests for a graphene oxide like sheet structure, which was then observed in the HRTM, which is in the further slides. And furthermore, we also study the UV vis, where to our fascination that the uncalcined sample did not show a broadband absorbance as it started absorbing only after 500 nanometers. However, the calcined sample showed a broadband absorbance, but the nickel doping actually improved the absorbance as well as it could extend up to 900 nanometers in wavelength range. So this is the HKSC and nickel HKSC calcined samples SEM images showing the octahedral structure of this HKSC crystals with some copper oxide particles embedded over it. Similarly, in the case of nickel HKSC, we can observe more number of particle formation, which is deposited over our crystals. Then this is the nickel HKSC calcined samples HRTM, which clearly shows the sheet-like structures embedding these copper oxide particles in them. So outcomes of this photothermal technology would be low cost production of water, reduced energy consumption, reduced pollution, thereby leading to a green initiative to suggest safer drinking water made highly accessible. And finally, this particular bar graph shows the fundings that are being acquired by various solar desalination projects globally, and it is currently in place or coming in the near future. So finally, I would like to acknowledge Professor Dr. O.P. Sinha sir, Dr. Jagjeevan Mittal sir, Dr. Ranu Nayak ma'am, and Dr. Nidhi Chauhan ma'am for giving me this opportunity to present in this excellent workshop. I would also like to extend my thanks to Dr. Sandeep Chakrabarti, Ms. Geetika Jain, Dr. Ranal Kanti Mandal, and Dr. Rajiv Ghosh Chaudhary for their help and support in my research.
Thank you, Abhyavarti, for this insightful talk. Now we can have some questions.
Okay, while Pooja is reading out, I would like to congratulate Mr. Abhyavarti Selvam. He's a very bright student from our institute, and good luck for your future, whatever you have achieved. I hope you achieve much more than this, what you have today. And you gave a very excellent talk talking about a very important topic about photothermal desalination technology. I know you and your mentor have been working in this topic. So this is definitely going to reduce the energy consumption as well as cost and the pollution. So really a practical problem that has been undertaken by you and your mentor to for I would say societal benefit. Congratulations. So Pooja, I think you could read the questions.
Yes, ma'am. From Chinmay Shukla, can the amount of water damp the overall plasmon activity?
See, okay, this is a good question, but the concept is about interfacial evaporation. So if we are focusing on bulk heating or also natural evaporation, then the whole water would be a problem because the material would be submerged inside the container in which we are doing the desalination. But since our materials or membranes are mostly focused on placed over the surface like floating membranes, so the water amount doesn't affect. It's actually more effective technology in this way.
Thank you. There is another question. That is there a difference in photothermal efficiency between Janus structure and reticular structure?
Yeah, actually the reticular materials are basically the solar absorbers. But the Janus structure is more of a membrane which helps with the concept of water pumping and salt rejection. So Janus is mostly focused for the water pumping and salt rejection factors. But adding reticular materials like MOFs or COFs will improve the photothermal part, the photothermal conversion part.
Thank you, Abhyavarti.
Thank you.
Ma'am, if there is
any other question from the panelists? Okay, if not, then let's thank Abhyavarti. And let us go back to our previous talk, which remained unfinished. So let's welcome back Dr. Kalavati Saini from Miranda House College. Ma'am, would you like to share your presentation one more time?
Okay. my screen is visible. Hello?
Your screen is visible, ma'am. Can you be a little bit louder?
Yeah, ma'am. The use of green synthesized nanomaterial for anti-cancer, anti-diabetic, and antibacterial applications. Just all application related to green synthesized zinc oxide nanomaterial. We have compared the result with chemical wet method synthesized zinc oxide characterization, and these are the anti-cancer, anti-diabetic, and antibacterial activity which perform with only green synthesized zinc oxide nanoparticle. Though we have done with other metal oxide, but here I am discussing only on zinc oxide nanoparticles. These are the plants which have been used in the synthesis. One more plant, that is the champa. Why green synthesized zinc oxide nanomaterial? As we know, the green synthesized material are synthesized with extract of plants parts like root, leaf, and stem, and other part also. All parts have the some particular phytochemical having different functional group which incorporate the specific property in the synthesized material, and they also act as a stabilizing as well as capping agent. And the green synthesized material are cheap like zinc oxide. We don't use any sophisticated chemicals, and these are the not hazardous also, and it is environmental friendly also. The anti-cancer activity we have performed with leaves part of the Azeritica indica, as it is very well known tree, and there are several phytochemical which are present in different part of this plants. Like azeriticin is some property, and the main anti-cancer property is presence of the quercetin in the leaf particle. Other property, presence of the other phytochemical like nimbin, nimbidine, nimbidol, sodium nimbinate, and other also. Why zinc oxide nanoparticle? As we synthesize with green method, the synthesized zinc oxide is n-type semiconductor, direct band gap, and the green synthesized nanomaterial have the band gap with the range 2.46 to 3.146 electron volt in our case. These are the highly biocompatible and shows different property. Our one student work on the supercapacitor as well as photocatalytic property of synthesis material, which I am not discussing here. And this is the, there are 2-3 papers from which I am discussing my PPT. These are the, we work on lung cell line, that is A459. And we vary the concentration of the extract of leaf of Azeritica indica, like with 1 ml, with 2 ml, 5 ml, and 10. I'm discussing only with 1 and 2 ml. One paper from chemical papers of Springer Nature, other materials today proceeding. This is the simple synthesis. We prepare leaf extract only in aqueous media in deionized water at 40 degree, and take the metals, salt, zinc sulfate as the precursors, and only with 2 hour stirring at only 40 degrees centigrade. With 1 ml, we have received the particle like road shape and characterization TCA, FTIR, powder XRD. Also for with 1 particle we did the XPS also, and we synthesize the anti-cancer activity, done the anti-cancer activity with only extract, chemical synthesized zinc oxide, that is with disodium citrate and NaOH, that is the chemical wet method, and the green synthesized method. The chemical wet synthesized zinc oxide doesn't show, any anti-cancer activity. Only extract shows anti-cancer activity, but the IC50 value is lesser than the zinc oxide, which is synthesized with either 1 ml, 2 ml, 5 ml, or 10 ml. When we increase the concentration of the extract, like with 1 ml, 2 ml, 5 ml, 10 ml, that IC50 value is decreased. And this is the another paper which is related to anti-diabetic activity. These are the plants flower where we have synthesized zinc oxide with only 1 ml and extract either antibacterial, anti-cancer, or anti-diabetic. In all cases, we have taken 25%. These are the results regarding 5 ml and 10 ml of leaf extract when zinc oxide is synthesized, and also only extract is used. And as a control, I have already explained, we have taken the zinc oxide, which is synthesized with chemical weight method, where as a stabilizing as well as a reducing agent, trisodium citrate is taken. This is the another paper which is regarding hyperthermia technique based, and this is not a green method, so I'm not discussing, and this is the particle also different. And these are the UV data by which either band gap also affecting the anti-cancer activity. UV spectrum, lambda max is obtained for 1 ml 370.01 nanometer, band gap is 2.50 electron volt. That is evaluated from top plots, and these are the XRD data. And for the presence of phytochemical, we have done the FTR analysis. With one particle, we did Raman also. These are again the XRD pattern regarding 1, 2 ml. And these are the, like, when we synthesize zinc oxide with chemical weight method, this is the lambda max with L2, previously was for 1 ml extract. This is with 2 ml. This is the band gap 2.46 electron volt for zinc oxide when synthesized with 2 ml, and this is 3.146 when synthesized with chemical weight method. This shows the presence of FTR analysis, phytochemical, and these are the XRD pattern. And in this case, the crystallinity of the particle is found very good. These crystals are, or powder material is very well stable, not hygroscopic, and with the time there is the intensity is not decreasing. We have did the with fresh synthesized nanoparticle also 1 year after, and also 2 year also, because the anti-cancer activity we are doing with geology department, University of Delhi, that does take too much time. So we check our stability after we have characterized like before 1 year, but we are finding the anti-cancer activity after 1 year. Then we want to know either our synthesized particle are in same characteristic physicochemical properties. So we did this experiment. These are the same images. These are the with chemical weight method, and these are with green synthesized matter. And the TG also important, which also shows the presence of the phytochemical in the synthesized zinc oxide nanoparticle. With changing the concentration of the extract, we have found the different morphology, and also we have found the IC50 value is different or decrease. These are the TAM images with green synthesized as well as with chemical weight method. EDS analysis shows the percentage composition of the zinc as well as oxygen in the synthesized material. These are the zeta potential value, which is very important when we study the surface property or we want to see the interaction with the biological material, with cell line or with antibacterial study also. If the, as we know, if the zeta potential is in the borderline range of -30 or plus millivolt, then the interaction with the cell line will take place. In our cases, the zeta potential is -28.64 millivolt for L2 nanoparticles and -34.75 for zinc oxide nanoparticles. These are the cell viability study. Cell viability has been studied with MTTSA, where we have raised the concentration of synthesized zinc oxide nanoparticle with 100 to 250 microgram per liter. These are the comparable study with control only phosphate saline buffer with chemical wet method synthesized zinc oxide, green one for only extract, and purple one like for at 100 microgram per ml concentration, 150, then 200 and 250. I'm skipping these parts. These are the first one with 2 ml extract and we synthesize 2 ml zinc oxide with 2 ml, and this is with 1 ml. The cell viability as well as IC50 value varies, and the same MTT we have done. For getting the change in morphology, we did crystal violet assay, and as we see, this is with control with buffer saline. This is with zinc oxide chemical wet method. This is with only extract. This is zinc oxide with extract. The cell are more killed with zinc oxide when synthesized with leaf extract. And these are with L2, the same. But the IC50 with L1, there was 138 something 0.63, and for L2, this is 130.95 microgram per ml. These are the morphological as well as apoptosis assay that is done with acridine orange as well as propydium iodide. There is the double staining is done. This is again with phosphate buffer saline. This is with zinc oxide chemical wet method. This is only extract, and these are the with zinc oxide with 2 ml. As we are seeing, more red fluorescent cell are seeing, which shows the more cell are killed. Here is the YC viable cell and EA early apoptosis and SN secondary necrosis stage, and the cell killing property of the green synthesized material found more than with only extract. And these are the flow cytometry. We have also see the different phases of cell growth that is also affected by this. These are the different percentage of cell G1, S, and C2. Again, A for phosphate buffer saline, B zinc oxide chemical wet method, and C only extract, and D with green synthesized zinc oxide. Here you are seeing the percentage ratio are changing with different type of the cell growth. This is again, you are seeing more red fluorescent cell or killed cell